지금부터 시작하도록 하겠습니다. 저희들이 계획식으로 시간을 잡아놓긴 했으나 지금 코로나 상태 때문에 내일도 별로 없고 해서 오늘 계획식은 회장님의 인사말로 시작을 할 것이고요. 또 1시부터 시작하는 국제 심포지엄부터 해서는 영어로 간단한 소개도 하고 연사분 소개도 하고 그리고 연사분들이 제출했던 다큐 파일들을 틀어주는 방식으로 하게 되어 있습니다. 여러분들은 지금 온라인으로 이것을 시청하게 될 것이고요. 일단 사태가 이렇게 돼서 저희들이 학회에서 준비하는데 많이 어려움이 있었으나 지금은 아마 우리나라 여기저기에서 여러분들이 지금 화면을 보고 있을 것이며 또 준비하시는 분들이 많은 것들을 열심히 준비했기 때문에 참 좋은 시간이 될 것이라고 생각이 됩니다. 먼저 그러면 우리 회장님을 모시고 회장님의 인사 말씀을 먼저 듣도록 하겠습니다. 한국토양비료학회 박만 회장님을 모시도록 하겠습니다.
토양비료학회장 박만입니다. 현재는 코로나가 1단계로 낮춰져 있긴 하지만 여전히 집단적인 모임이나 다수의 활동이 약간 위축되어 있습니다. 그리고 저도 지금 이 회의장에는 많은 분이 안 계시기 때문에 마이크를 꽂고 인사를 드리도록 하겠습니다. 코로나19가 참 많은 것을 바꿨습니다. 저도 어떻게 해야 될지 모르는 상황에서 또 아시다시피 학회장은 1년입니다. 1년 동안 많이 다니고 활성화하고 해야 되지만 그런 점이 거의 부족하고 또 할 수 없었던 점을 양해를 부탁드리겠습니다. 저의 코로나19 사태가 아직 종결되지 않은 상황 속에서 한국토양비료학회님의 열정과 관련 연구자분들의 많은 관심 속에서 이번 학술대회가 비록 온라인이긴 하지만 주로 온라인입니다. 온라인으로 그래도 성황리 개최될 수 있어서 모든 참가자 여러분께 감사드리면서 환영 인사 올립니다. 또한 본 학술대회를 지원하는 한국연구재단, 농촌진흥청 등을 비롯한 다양한 후원기관, 회사 및 단체분들에게 고마움을 전합니다. 이번 학술대회는 코로나19의 잠재적인 우려 상황 속에서 참가자분들의 안전 확보와 학술 활동의 극대화를 동시에 만족하고자 많은 고민을 해왔고, 그래서 지금 현재 하나의 방법으로 최소의 현장과 대부분의 온라인 발표로 진행하게 된 점 양해 부탁을 드리겠습니다. 이상 기후변화와 더불어 각종 신종 질병의 확산은 인류의 현실적인 위협으로 대두되었습니다. 이러한 위협들은 수많은 복합적인 요인들에 의하여 발생되고 있어서 다양한 방면에서 예방과 예측의 강구가 시급한 시점입니다. 잘 알려진 바와 같이 토양은 기후변화뿐만 아니라 모든 생물의 생육과 다양성에 직접 간접적으로 지대한 영향을 미치고 있습니다. 토양의 본질성과 생물의 다양성을 하나의 핵심 분야로 활동하는 우리 학회는 이번 학술대회를 계기로 학문적, 산업적, 사회적 역할을 더욱 확대하고 확고히 할 수 있는 또 다른 기반을 마련하고자 합니다. 특히 이번 학술대회에서는 우산 석고의 농업적 활용 확대 심포지움과 병행하게 진행되고 있어서 산업 부산물의 친환경적 재활용 관련 연구에 대한 관심을 더욱더 증대시킬 것으로 기대합니다. 더불어 토양, 비료와 관련된 새로운 도전 분야, 기존의 발전된 연구 결과, 다각적인 이론과 해석, 응용성 입장 등 참가자들의 축적된 노력과 의견들을 마음껏 펼치시고 교류할 수 있는 축제의 장이 될 수 있도록 희망합니다. 이번 학회는 참가하시는 모든 분들이 짐작하시다시피 우여곡절 끝에 개최되었습니다. 실제 시간과 장소, 방식을 정하는 데 있어서 굉장히 많은 고민을 하였습니다. 그럼에도 불구하고 비록 제한적 소통 방식이 될 수는 있겠지만 참가자분들의 연구개발의 연속성과 확장성이 위축되지 않는 학술대회를 만들고 즐기시기를 다시 한번 부탁드립니다. 더욱더 풍성하고 고대되는 차기 학술대회에서 이번과 좀 달리 예전처럼 건강하고 행복한 모습으로 모든 참가자분들이 호응할 수 있기를 간절히 바랍니다. 감사합니다.
Hello, ladies and gentlemen. It is my great pleasure to welcome all the participants to 2020 International Symposium focusing on production and reduction strategies of fine particulate matter in agriculture. I'm very sorry that this symposium is to be held mostly online because of the persistent pandemic, COVID-19. As you might know, COVID-19 has brought very tough times for everyone. In fact, it was not easy to decide the right time and place, the method of proceeding the symposium, participating organizations, and sponsoring agencies, and so on. Nevertheless, thanks to your strong desire for research and scientific inquiry, many fresh and recognized researchers finally get together from many countries. And also we are fortunate enough to get supported by National Foundation of Korea and a group of sponsoring agencies with whom we will interact in the conference. Today's main topic is fine particulate matter. As well known, agricultural emissions play a leading role in its formation in various regions of the world, mostly related to animal husbandry and fertilizer use. And other minor contributions come from burning of crop residues and cultivation practices. A key component leading to particulate matter is ammonia. Therefore, our programs also focuses on agricultural emission and reduction of ammonia. These topics will be delivered by many speakers from USA, Germany, China, Japan, and so on. Of course, There are several other closely related topics, including agricultural dynamics and management of nitrogen, the impact on health, etc. The speakers in the program are uniquely placed to debate, discuss, and highlight the key points, trends, and reforms in the system for the on-site and online audience. I'm sure that our programs provide not only fruitful information but also strong motivation for scientific societal exchange. Please be entertained with all the events of this symposium. Thank you very much. I hope you all enjoy this exciting symposium.
Hello everyone, this is Kim. Let us start the International Symposium 2020 held by Korean Society of Soil Science and Photography. Because of the international pandemic situation, we are doing this International Symposium by online, so you will watch it through the online. We have 14 speakers from the abroad and from the Korea as well. And this symposium is separated in 2 sessions. In first session, we have got 7 speakers. And in the second session, we also have got 7 speakers. The topic of this international symposium is production and reduction strategies of fine particle methods in agricultural program schedule. Every speakers will spend 15 minutes for their speaking, and we have no Q&A times in this system. So, okay, then let's start from the first speaker. I'm going to invite the first speaker. His name is Sun-tae Kim from Korea. He's going to talk about the Korean current status of PM 2.5 and the importance of ammonia emission in South Korea. Please join with me to welcome Sun-tae Kim.
Hello, I'm Sun-tae Kim at the university. I'm glad to have this opportunity to present our research outcomes. Today's title is Current Status of PM 2.5 and the importance of ammonia emissions in South Korea. In South Korea, we have so-called super site where we are measuring PM 2.5 concentration and its compositions. I'm showing 2 super sites here. One is located in Gangneung Island. One is in Ulsan in Seoul. So when you get the annual trend of PM 2.5 concentration from those 2 super sites, you can see some descending trend. And then when you look at the slope at the Bulgar is somewhat higher than that of the Penguin Highway. Still, Bulgar, the salt PM2.5 concentrations is higher than those from the Penguin Highway. Let's look at the left diagram. In diagram, it shows PM 2.5 concentrations for each province in South Korea. When you look at the south, during the year 2016, the annual mean PM 2.5 concentration was 26 microgram per cubic meter. You can see the yellow dotted line. That is Korean air quality standard. The value is 15 microgram per cubic meter. To satisfy our national air quality standard in Seoul, actually not the same for other provinces, we have to reduce at least 1/3 of our PM2.5 concentrations. On the other hand, you can see the white color dotted line, that is WHO air quality guidance for PM2.5. The value is 10 microgram per cubic meter. To satisfy WHO's guidance, we have to reduce PM2.5 concentrations by about 2/3. That's require a lot of our effort to reduce our emissions and to understand our circumstances. When you look at the PM2.5 concentrations over Beijing and Shaanxi in China, the values are around 50. So compared to South Korea, the PM2.5 concentrations, it's still China's PM2.5 concentrations are much higher than the South Korean ones. That's why our situation can influence the downing South Korean PM2.5 concentrations. That's why they are really concerned about long-range transport of PM2.5 and its precursors. When you look at the right diagram, it explains the costs. There are two types of costs. One is past cost. If we don't reduce or improve air quality, some people will be hospitalized or the mortality will increase. That is past cost. On the other hand, to reduce the emission of air pollutant in the atmosphere, we have to install and maintain the flue gas treatment system. To operate the kind of emission control devices, it requires cost. That is industrial cost, I can say. So our goal is how to set the optimized cost for our society. If we don't reduce the emission of air pollutants, we will pay more hospital or the health cost. On the other hand, they regulate too much to keep to protect our health, then the industrial cost increase abruptly. That is kind of important thing. One thing I mentioned with this left diagram, we have to reduce a lot of the emissions from South Korea or Northeast Asia. So when you look at the south, we have to reduce 11 microgram per cubic meter to satisfy our special standard. So how much does it cost? That is our concern. And our estimation is to reduce 1 microgram of PM2.5, it costs about $2 million US. So 11 microgram means about $25 million for every year, every 5 years. This pie chart shows how PM2.5 is composed. In PM2.5, we have measured 5 categories. The first one is inorganic ions, and second, organic carbon, and third one is enriched carbon. Also, we have crystal substances and minerals. The inorganic ions are major components of PM2.5. In our country, South Korea, about 40% of PM2.5 is inorganic ions. During high PM days, the rate, composition rate of inorganic ions increases up to 60%. That's a lot. So that's why these inorganic ions are the main ingredient of PM2.5. That's why our government wants to regulate the concentration by reducing vehicle exhaust and by removing old coal-fired and power plants. In summer, then we have lots of vehicles. Through the combustion process in engine, they are emitting lots of the oxide of nitrogen, so-called NOx. NOx, once they release into the atmosphere, through the oxidation process, they form nitrous gas, HNO3. And then this nitrous gas becomes the nitrate NO3 minus. That is one of the major ingredients of inorganic ions. In the power plants, they are burning lots of coals. In coal, we have sulfur, and then during the combustion process, sulfur becomes the SO2 salts. Also, the salts emitted into the atmosphere through the oxidation process, they becomes sulfate, SO2 minus. So when they release from the original emission sources like vehicle and the stacks of power plant, they are gases or vapor. But through the oxidation process, those gases are converted into particles. So gas particle conversions are quite important. Also, when you look at the composition of PM2.5, I didn't present it here, but we have the water layer. So water layer is kind of surrounding, encompassing the PM2.5, and once nitrate and sulfate are formed, they are dissolved into those kind of water. We call the water particle water. So we know that the nitrate and sulfate, they are anions. So as those concentrations increase, pH will drop. Once pH became too low, the gas to particle conversion will stop because they cannot fall under certain pH range. If pH range is too low, we can not expect gas to particle conversion anymore. But in our atmosphere, in those 6 states in South Korea, we have lots of cations like ammonium. Ammonium gas is coming from ammonia gas. They are dissolved into water very well. That's why once the ammonia gas exists in the air, then it can convert it into ammonium anytime. Their concentrations are 5 to 10 ppb in Seoul area. That's a high concentration compared to other species. That's why many people consider by reducing the ammonia emissions, we can reduce the formation of ammonium. That's why, and then we can somehow maintain the average of pH at low. Then we can start further formation of the average. That's why many people are interested in how to regulate ammonia and then the effect of this. This diagram also shows why ammonia is important to determine PM 2.5 concentrations. These green colors displays the precursors of PM 2.5, that means the ingredients of PM 2.5. And this orange color represents the PM 2.5 composition. We have quite different composition, like as I mentioned with pie chart, we have organic part and we have an inorganic part here. And then we have NOx and SOx. They are gases, they are not particles, but through this kind of oxidation process with the radical or ozone, they are forming nitric acid gas and sulfate, and then they are combined with ammonia, and then there becomes ammonium nitrate and ammonium sulfate. Yep. Again, they are more than half in South Korea, and you get the PM 2.5 composition. That's why the ammonia plays a critical role to determine PM 2.5 concentration in Northeast Asia, including South Korea. That's why, again, many people consider the regulation on ammonia emissions are quite important. So where we have the ammonia emission, that is kind of important in the plan. In South Korea, the Ministry of Environment, they estimate national emissions for NOx, SOx, dioxin, and ammonia every year. When we look at the Korean emissions inventory, they say the agriculture is the main emitter of the ammonia. About 80% of ammonia in South Korea emitted from agricultural activity, like the fertilizer use and stocks manure. Some research is also mentioning automobiles are emitting the ammonia gas, but still the ammonia emission rate is somehow much more than the agricultural activities. Also, ammonia can be emitted into the atmosphere through ammonia split from the CCL, selective catalytic reactor. To reduce NOx emissions, many plants and facilities, they are adopting the so-called SCL, selective catalytic reduction devices. They are adding ammonia as a catalyst, but to keep the efficiency high, they are adding ammonia, the catalyst, more than the stoichiometric rate. So that means some portion of the input, ammonia input, can be released into the atmosphere. That is the ammonia split. Still, we don't know yet how much ammonia split we have in South Korea. Also, ammonia can be used as coolants. That's why but I think the ammonia use as a kind of coolant is important, but still, it's not clear how much we are using the ammonia for the purpose. This is summary of my talk today. When you look at the PM 2.5 concentration in South Korea, the is much higher than our national standard. To satisfy the annual goal, we have to reduce about 50% of our current emissions. When you look at the PM2.5 composition, we have inorganic species like sulfate, nitrate, ammonia. For them, the pH of after-bound water is quite important because if those anions, sulfate and nitrate, lower the pH of after-bound water, PM2.5, the particle, the aerosol, cannot process the additional formation of sulfate and nitrate. But important thing is we have plenty of cations like ammonia in Northeast Asia. That's why we are suffering from high PM2.5 concentrations every winter. But some researchers have, by reducing ammonia or ammonia emissions, we can reduce concentrations of PM2.5. The Korean Ministry of Environment, they are estimating about 75% of ammonia is emitted from agricultural activities, but still there are potential emitters like automobiles and the refrigerator and the SCCS slip. There are much of the candidate of ammonia emissions, but we still don't know yet how much they are emitting ammonia in the atmosphere. So, as a future work, including the long-range transport of PM2.5, we have to check the uncertainties in the emissions inventory, and then intensive observation and investigation on the rate of ammonia gas in North Asia is attended required. Thank you.
Good morning, everyone.
Okay, it's time to invite second speaker, but because of the straight timeline, I think we have got around 2 minutes break between the speak to get refreshed. So I just like to have got 2 minutes refresh before we have another speaker. Okay then, let's start the second speaker. I'm going to invite Pilju Kim from Korea also. He's working on Gyeongsang National University and he has worked on the methane and greenhouse gas stuff for his life. His topic is high ammonia emission and integrated nitrogen management plan to reduce high ammonia budget in Korea cropping sectors. Okay,
Okay, thank you so much. My name is Kim at Gyeongsang National University, and today just I will talk the Korean ammonia emission. Maybe you can guess from the title. We have the very high ammonia emission here. Lastly, I will discuss how we can decrease this high emission in Korea. And this is the nitrogen dynamics in the soil ecosystem. Very complicated cycling, like fixation, the mineralization, and nitrification, denitrification. However, from an organic nitrogen, this can convert into ammonia. Depending on the oxygen concentration, depending on the soil pH, some ammonium can go to ammonia. Today, just I will focus on this ammonia emission here. This is my study. We are studying some nitrogen balance or nutrient balance in the rice paddy. I applied 110 kg of nitrogen per hectare. However, among them only less than 30% of nitrogen obtained by plant, meaning 70% nitrogen cannot back in the environment. For example, approximately 40% of nitrogen can go to the water body, to the groundwater and the surface water, and also can emit into ammonia. However, this is very huge levels of the nitrogen is volatilized into ammonia. This cannot back atmosphere environment as well. Also, some of them can convert into nitrous oxide. This is very important greenhouse gases. And this is very basic things. This ammonia. Why this is important? This is the ammonia that volatilized from the soil, and then how this is a precursor of the PM 2.5. With the PM 2.5 is particulate matter having less than 2.5 micrometer. Directly can affect our inside, okay? And then also this is ammonia emitted can acidify soil. This is very important, can affect the global ecosystem. And then to understand our situation, how much we are applying nitrogen, first of all, we need something official data. This is produced by OECD. Even though this is our data is produced by Korean scientists, however, comparable with OECD countries. And then average nitrogen balance meaning the difference between nitrogen input and output. This can be surplus, can get surplus in the surface area. However, average of the OECD country only 65 kg per hectare. But our country, highest of nitrogen in the OECD countries. There are several things. We have the first ranking in the world. One of them is nitrogen balance. Nutrient balance, we are marked the first in the world. Oh, this is a very terrible thing, okay? This is not comparable with the Netherlands. This is not comparable with Japan, okay? Meaning, this high nitrogen meaning we have something potential environment pollution by released nitrogen. And then even I'm studying this balance approximately 30 years. However, our nitrogen balance was not changed in the last approximately 30 years. Only fluctuated depending on the years. However, in the different countries like the Netherlands, this is the highest nitrogen consumption country, and then last 30 years ago, they have 2 times higher than Korea. However, their nitrogen balance significantly decreased with the time pass. In this sense, their level is less than half of the Korea. This meaning they tried very strongly such regulation and make them some penalty. However, still Korea is not decreased. Meaning this we have a very serious critical problem here. And then basically why we have a very high nutrient balance, nitrogen balance, there are 2 points we can questionable. One is high input, the other one less output. We need something like analysis. However, still we have very high input. And then total balance, total input nitrogen nationally is slightly decreased. However, this is caused by nitrogen decrease, not manure decrease. In contrast, the other side, manure production, slightly increased. This is very comparable. Approximately 30 years ago, only covered by 30% by manure. How recently, this is grow up to the 50%. I mean, without the decreasing manure industry, it's not easy to decrease our nitrogen balance. This is a real situation, okay? And also, however, among them, surplus, balance, can be several contamination sources, okay? Can guess how much you have the nitrogen contamination. One of them is ammonia. Ammonia is very interesting molecule. Even this very small molecule weight they have, however, high solubility they have. They are contact with the water immediately. More than 30% of the ammonia solubilized in the water. And meaning something under the water condition might be like dynamics, could be slightly different. Totally, they have the same point. This ammonia emission very depends on critically by pH. This is controlled by pH. In particular, in the alkaline condition, most of the ammonium nitrogen, inorganic ammonium nitrogen, convert into ammonia and then go to the atmosphere. We call this is ammonia volatilization. Meaning to decrease ammonia, absolutely we need firstly decrease of soil pH. This can be one of the strategies. And then something grab is some problem. However, the track you can check here. In Korea, ammonia emission source can be saved in agricultural sector. There are two sectors, like fertilizers in the cropping land. The other one, livestock manure. This comes from the animal feeding sector. Totally, in the whole industry, our total emission, ammonia, is a slight increase. Unfortunately, agricultural ammonia contribute approximately 70%. However, this contribution increases slightly to 2015, approximately 80%. Meaning, to decrease our total ammonia emission, contamination, absolutely, we need something agricultural contribution here. Without agricultural decrease, not easy to solve this problem. And then already I said, and then this is the main high ammonia emission. We can guess this comes from the high input, high nitrogen production. Among the chemical fertilizer and the manure was the main contributor. But interestingly, there are two sectors contributed in the agricultural sector. One is livestock, the other one fertilizers. Already I said, this is the main nitrogen production or applications sector. However, most of them come from the livestock. Only 20% in the 2004 coming from fertilizer based. But terribly, with the time pass, this proportion by livestock dramatically increased. Lastly, more than 90% of ammonia come from the livestock manure. This meaning to decrease ammonia emission. Absolutely, we need to control this industry scale or industrial density of the livestock. First of all, we need something understanding. Okay, I think this is coming from the OECD. Some data can have some problem, but still, this is we only can guess from the OECD data. Okay, and then as a scientist, I am thinking why it is like happening here. This is a real situation or we have some problem in calculation. Something every day I am thinking, and I need something analyzing. Which factor directly affect our higher ammonia emission? First of all, this is I compared some nitrogen flux of available land, meaning only from the available land emitted ammonia. How much they contribute here? However, in the OECD data is not comparable with other members. But just though in OECD country, even though Australia, Chile, Japan data, the New Zealand data was listed here, however, other country, OECD country, average they emit 7.5 kg ammonia per hectare. However, surprisingly, our country, more than 130 kg of ammonia emitted from agricultural sector. So I am curious here. This is real happening, or we have some problem on calculation. Okay, we need to verify. If this is real happening, we need more active something measures to decrease this ammonia emission from the agricultural sector. Okay, and then this is basic in greenhouse gas emission flux calculation or ammonia flux calculation is the same methodology we use. First of all, ammonia flux, we should consider activity. What's the activity? Activity meaning here, nitrogen fertilizer consumption ratio. The other one, nitrogen content. The other very important factor is emission factor, ammonia emission factor. We applied 100 kg nitrogen, how much proportion go to ammonia? This is what we call emission factor. However, in my side, I'm analyzing something problem. Why is like happening here? I think first of all, our calculation, they have a big uncertainty in Korean cropping land. First of all, activity is not clear. There are no natural statistics to the nitrogen fertilization level in rice paddy. In upland, some specific crops like maize, like the land. How much of the nitrogen we are applied, not clear. Okay? First, the problem can come from here. Second, emission factor was developed by my former scientist, but in my thinking, this emission factor still have something problem. Urea, they proposed approximately 14% of nitrogen go to the ammonium. And the complex nitrogen fertilizer, meaning the NPK together, they have the 7.5% of the ammonia applied nitrogen added into ammonia. I think this calculation also can have some problem in the cropping sector. Might be livestock feeding industry, they have the more big uncertainty that they can have. They need something analysis. And then this is a basic emission factor. Even different country, USA, they have the, depending on the different source of the nitrogen, ammonium nitrogen fertilizer, already they have some emission factor. And previously, before 2013, we used to USA data. And even European country, depending on the location, climate condition, depending on some countries, they have the different emission factor, default value they have. Only Korea, in cropping land, we developed 2 emission factor, like urea. They proposed 14% of the applied nitrogen converted into ammonia. And then complex fertilizer, 7.5% of nitrogen, it can be converted into the ammonia. In my thinking, we need something checking here. Okay, first of all, even the rice paddy soil, upland soil, they have a big different environment condition, ecosystem condition. Might be ammonia emission rate factor could be a bit different. However, they are not distinguished between 2 soils. The other one, they studied some emission factor. However, in my thinking, this is not acceptable. Big difference between urea and complex fertilizer. This is based on same nitrogen content. Same nitrogen content can have the similar emission factor. Meaning I applied 1 kg. In case of even this is mixed or single, maybe I think there are no big difference with nitrogen emission factor. And then here already we have something catching what problem we have here, and then I did something First of all, how much ammonia emission have, understanding. Secondly, we need something developing, strategy. Can decrease ammonia emission here. And here, I am developing our national emission factor in rice paddy. In the two study, something ammonia emission rate, something protocol developing is very, very important. In the university, there are two main techniques. One is enclosure techniques. This is basic, okay? We are catching ammonia in the acidic solution. But still have several something limitation, this program, this methodology. However, this is a typical and then most old method, this basic. And then recently, because this is analyzing, we need high time consumption and labor consumption we need. And then we want to minimize something labor investment. In case of this one, we are developing micro-meteorological techniques, like something mass balance, and correlation, gradient methodology. However, in case of this one, we need some detector, something automatic detector we need, meaning high cost is required here. In my expectation, in the future, like almost technique will go to this direction from here, okay? However, in my analyzing something even wonderfully developed techniques, however, they have something strengths and weakness, like the static method, chamber method, or dynamic chamber method. This meaning static chamber method, very simple, passively we are sampling, okay? So something emit, catching, analyzing. Active meaning we are, there's some blowing, uptake, and then OD in H2 solution, okay? And then here we can study long-term study, because there don't need any electrics. However, here electrics or some instruments essential. And then in this case, cumulative sampling or this is representative sampling, there are different methodologies they have. This meaning in here strengths meaning continuous sampling. There are no real losses here. However, weakness, there are strong chamber effect. Chamber effect meaning inside the chamber can be different environment out of the chamber. Okay, higher temperature, not the something winding. However, in the dynamic chamber, high efficiency they have, but main problem is the high cost. And then we need something the electrics. But I am compare which is more high efficiency they have. There are two methodologies I proposed. One is the static chamber, the other one dynamic chamber. In my study, dynamic chamber with increasing the blowing rate, this efficiency slightly significantly increased. But in my study, in rice paddy, static chamber more highly efficient, highly catchy something emitted ammonia here. We are decided, we are select this one, okay, static chamber, and go to the field. And then we are determining the dynamics of the ammonia emission during the rice cropping season. Already this is well known. We are after application nitrogen. Immediately, this is the ammonia concentration jump up. And then with the decreasing ammonium nitrogen in soil, dramatically decrease also. Meaning we are 3 times splitting of nitrogen. Basal 1 second. Just after the application, ammonia emission sharply increased. And then cumulative of a year or some seasonal, we can say this is flux. Okay? In case of this is slope, depending on with the increasing application level, ammonia volatilization flux significantly and highly increased with some strong correlation. And meaning 39%, approximately 40% of the applied nitrogen is emitted into ammonia in rice paddy. First year study. I really wonder this high emission level. We need did more 2 years study here, still study, okay? And then this is some comparable. In my first year's study, we observed approximately 40% of nitrogen is gone into ammonia. But in China, they are studying some meta-analysis and then merge it together in rice paddy. They are expecting approximately 80% of applied nitrogen is gone into ammonia. This is not small. Okay, this is very big, understand. We need something strong and active activity to reduce ammonia emission here. And then also our government catching what program we have, and then they make the goal to reduce methane emission. Like something based on over the 2016, lastly, in the next year, we want to decrease, we will decrease 30% of the ammonia emission. Also, they support some financially support program, such as in the livestock feeding stock main ammonia emission source. There are something supply microbial amendment, something during management of the manure, and then some preventive infrastructure that are supporting, like something bio-cotton, misting facility, make a mist, okay, and catching ammonia. However, in cropping sector, was not comparable with something like livestock sector, we are trying to some decrease chemical fertilization level from 270 kg to 235 kg up to 2020s. And then for this one, we are more positively, more actively supply slow release fertilizer. Okay, and then the other one, we try to expanding environmental friendly farming area to 8%. And then some strategy we are introduced here. Okay, my presentation is here. Thank you so much.
여기 쓰는 사람 그렇지. 이거 해놔야 되는데. Professor Dini Aneja. The title is Fine Particle Matter and Ammonia Pollution from Agriculture, Integrated Ground Waste Management and Satellite retrieval. Okay, welcome, Professor Dini Aneja.
Good day. Good day. My name is Vinay Aneja. What I'm going to share with you today is our ongoing research connecting integrated ground-based measurements and satellite retrievals with a view to predict fine particulate matter PM2.5 in rural areas where there is intensive agriculture, principally emissions of ammonia. I'd like to acknowledge my co-authors, Rebecca Wiegand, William Batty, and Casey Bray. All of them are my former graduate students. Intensive agriculture is an important part of the global, US, and North Carolina economies. Large emissions of ammonia gas emanates from the use of synthetic fertilizer and handling of animal waste. These emissions contribute to the formation of secondary fine particulate matter, which is PM2.5, causing a variety of human health and environmental effects. Therefore, the objective of this research is to examine the global, US, and North Carolina relationships between agricultural ammonia emissions and PM2.5 concentrations. And using North Carolina as a case study, we have developed a multiple linear regression model to predict ground-based levels of PM2.5 concentrations from 2008 to 2017. So, what are some of the emissions from agricultural operations? First, ammonia. Almost 80% of ammonia in the US atmosphere comes from agricultural operations. Oxides of nitrogen, 20%. Reduced sulfur compounds remains unquantified. PM2.5 direct emissions from agricultural operations is about 16%. PM10 is 18%. Methane and nitrous oxide, both of which are greenhouse gases, are 29% and 72% respectively. Odor and pathogens from agricultural operations, principally animal agricultural operations, remains unquantified. So as part of this research, we are going to examine PM2.5 secondary formation from intensive agricultural operations. So particulate matter 2.5 impacts human health and the environment, principally visibility. Most common ammonia reactions involve oxidation products of sulfur dioxide and NOx, which normally results in PM2.5, and this is what we call gas to particle conversion. Previous PM2.5 reduction strategies have focused mainly on the reduction of SO2 and NOx through the Clean Smokestacks Act and improved vehicle emissions. However, recent studies have indicated that a reduction in ammonia may have a positive effect on PM2.5 concentration. That is to say, if we reduce ammonia concentrations, in the atmosphere, PM 2.5 concentrations will also reduce. And how does this reaction takes place between ammonia and the formation of fine particulate matter, which is called gas to particle conversion? Ammonia in the atmosphere, which comes principally from agricultural operation, reacts with sulfuric acid in the atmosphere. It can be in the gas phase or the liquid phase to produce ammonium bisulfate, which reacts with more of ammonia to produce ammonium sulfate. So what do we see? The ammonia, which is a gas, sulfuric acid, which could be a gas, reacts in the atmosphere to form ammonium sulfate. Keep in mind, ammonia is the principal basic species in the atmosphere. The second reaction, that gas to particle, is ammonia reacts with nitric acid to form ammonium nitrate. Ammonia reacts with hydrochloric acid to form ammonium chloride. There is some reaction between ammonia and hydroxyl radical, but it's relatively a slow and relatively a marginal reaction to produce the amide radical. So these three reactions principally are the ones that we need to focus on, which is gas to particle conversion. Now let's examine the global comparison between ammonia emissions from agricultural operations and PM 2.5 concentration. And this map shows us a global map of ammonia emissions from agricultural soils. And here is the index shown right here. More red you have, more emissions of ammonia are taking place from agricultural soils. On the second map that we have is PM 2.5 concentration, which I obtained from the Edgar website. And so let's examine these two maps. Predominantly, ammonia emissions are occurring in the Indo-Gangetic Plain, which is the breadbasket of India, eastern part of China and the central plains of China, midwestern part of US, some in Europe. Now let's look at how does ammonia emissions from these agricultural soils relate to PM 2.5 concentrations in the atmosphere. And what we see is where there is large ammonia emissions, there is large PM 2.5 concentration. This is PM 2.5 concentration in the Indo-Gangetic Plain. PM 2.5 concentration, high PM 2.5 concentration, eastern and the central plains of China, midwestern part of US, and some in Europe. So what we see is there is distinctly a relationship between ammonia emissions from agricultural soils and PM 2.5 concentration. Now let us zoom down to just the US. US comparison between ammonia emissions from agricultural soils and PM 2.5 concentration. This map gives us ammonia emissions from agricultural soils in the US. And here is the index. More red and brown it gets, more are the emissions of ammonia. Now, on the right side, we have PM 2.5 concentration. Again, more red and brown it gets, more are the concentrations that are produced of PM 2.5 concentration in the units of micrograms per meter cube. And what we see is in the US, agricultural operations are principally both animal and crop agriculture are in the Midwest, in eastern part of North Carolina, and this is the state of North Carolina, and southern part of the state of Pennsylvania. That's where principal ammonia emissions are taking place, because that's where principally we have both crop and animal agriculture. And what do we see as we examine the PM 2.5 concentration? Downwind of Midwest, large PM 2.5 concentrations are observed, and in North Carolina, eastern part of North Carolina, and southern part of the state of Pennsylvania. So once again, we see ammonia emissions from agricultural soils have a direct impact on PM 2.5 concentration. So here is a map that gives us inorganic nitrogen wet deposition from ammonium. And ammonium in rainfall comes from ammonia emissions into the atmosphere. And what do we see? We see large ammonium deposition in the Midwest, which is where large ammonia emissions are taking place, and ammonium deposition in eastern part of North Carolina. This is the state of North Carolina on the mid-Atlantic part of the US. And this is the state of Pennsylvania. And we see ammonium deposition in the southern part of the state of Pennsylvania. So now we are going to focus on the state of North Carolina as a case study to see if utilizing satellite observations and ground-based measurements to develop a model that can predict PM 2.5 concentrations in rural areas of North Carolina. So the objective of this presentation is to use remotely sensed data, principally ammonia and aerosol optical depth, AOD, and ground-based meteorological and PM 2.5 data to produce a multiple linear regression model to accurately predict PM 2.5 concentration in areas with intensive agriculture and no ground-based PM 2.5 measurements. So the remotely sensed products that we have used, first, infrared atmospheric sounding interferometer IASI. It is a European-based satellite product, and IASI is known for its column ammonia concentration retrievals. And over North Carolina, the IASI satellite makes two passes, one at 10 a.m. and one at 10 p.m. And this study used the 10 a.m. pass to examine the ammonia retrieval. The retrievals are then passed through an algorithm to calculate ammonia column concentration in the atmosphere. The second product we used was from the moderate resolution imaging spectrodiometer, MODIS, which is a US-based NASA product. It came into existence in 1999. MODIS is most commonly known for aerosol optical depth, AOD retrievals, and it gives us 10 kilometers by 10 kilometer measurements. So we used two products, one for ammonia, which came from the IASI satellite, and the other for the aerosol optical depth, which is an indicator of total aerosol column loading from the MODIS satellite in the US. Here is what the products look like for one day, 2011, in the summer of 2011, remotely sensed over North Carolina. So this is the state of North Carolina, and we see the product giving us aerosol optical depth from the MODIS satellite. Here is the product from IASI, column ammonia concentrations, and what do we see? Eastern part of the state of North Carolina, we see large ammonia concentrations as measured by the IASI column ammonia concentration, again for the same year, 2011. But as part of this study, we have analyzed from 2008 to 2017, both the AOD and the ammonia column concentrations, and developed our model. So ammonia emissions, where was the model developed for, and the satellite observations. And so the model locations were based on measurements made at Cumberland County in the state of North Carolina and Johnston County in the state of North Carolina. And this is eastern part of the state of North Carolina with intensive agriculture, both animal and crop. Then we applied it to 3 different ecosystems: 1, intensive agriculture; 2, along the coast, marine environment; and 3, more inland with less agriculture. And then we tried to examine for another location what if there are any exceedances occurring in these intensive agricultural locations for PM 2.5. So the validation sites were Duplin County, which is intensive agriculture, New Hanover County, which is a marine environment influenced by marine air, and Catawba County, which is away from agricultural operations predominantly, and then applied also to Sampson County to see if there are any exceedances of a PM 2.5 in a rural environment. So the statistical model development was based on SAS, using the satellite ammonia concentration, which is IASI, and aerosol retrieval, which is MODIS, and ground-based meteorology data and PM 2.5 concentration from stations in Cumberland and Johnston counties, as I indicated a little while ago, both located in the eastern part of the state of North Carolina. Using statistical analysis softwares, SAS version 9.4, a multiple linear regression model was built. And the multiple linear regression model that we derived based on SAS for PM 2.5 prediction is PM 2.5 concentration is equal to exponent of 15.14 times a constant times ammonia concentration, which is derived from ammonia retrievals from IASI, the AOD, which was derived from aerosol optical depth, which was retrieved from MODIS, and then ground-based measurements of temperature in degrees centigrade, pressure in millibars, wind speed in meters per second, and relative humidity in percent. So this is the model that gave us the best fit for the data as shown right here. So observed PM 2.5 axis for Johnston County, Cumberland County, and Cumberland and Johnston counties combined, which is where the two counties on which the model was developed. It's predicting the PM 2.5 concentrations, which are shown on the y-axis. So the red line indicates one-to-one line, and blue line indicates the line of best fit. And what we see is that the R squared is between 0.4 and 0.5, which is considered very good for observed data out in the field. So this is what the model was developed on. We then applied the model, and we then tested the model in Duplin County, this is the map of North Carolina. This is Duplin County, again, an intensive agricultural environment. And this is observed PM 2.5, and this is predicted PM 2.5, predicted based on the model. And what do we see? This is one standard deviation lines that are shown right here. The R squared is about 0.46. So the model is predicting another intensive location, agricultural locations rather well. When we applied it to another ecosystem, which is the marine environment, which is the New Hanover County along the coast, the robustness of the model was about 0.3 R squared. And again, what we see is observed PM 2.5 on the x-axis and predicted PM 2.5 on the y-axis. We then applied this model to Catawba County, which is all the way on the western part of the state of North Carolina with limited agricultural activity. And again, the model was reasonably good. Observed PM 2.5 and predicted PM 2.5, R squared was 0.3. We then applied the model to an intensive agricultural operation where there is no PM 2.5 data available. And what we saw was predicted PM 2.5 concentration for Sampson County, which is located in intensive agricultural operation right here. And what we see is that there are 6 PM 2.5 exceedances over the 9-year period between 2008 to 2017. And the US EPA's 24-hour primary and secondary standard for PM2.5 is 35 micrograms per meter cubed. So indeed, satellite observations and ground-based meteorological observations, which helped develop the model, allows us to predict if there have been any exceedances, since there are no ground-based measurements of PM2.5. And indeed, we saw that there are exceedances of PM2.5 in these rural environments. So in conclusion, ammonia emissions from agricultural sources play a role in PM2.5 concentrations. The North Carolina case study indicates the potential for predicting PM2.5 values, particularly in intensive agriculture areas, using satellite-derived products of ammonia and aerosol optical depth and ground-based measurements of metrology. Ammonia reductions could be a viable way to further reduce PM2.5 concentrations, even in rural environments. I'd like to offer my acknowledgement to the funding agency, Geophysical Fluid Dynamics Laboratory of National Oceanic and Atmospheric Administration, my graduate student, Albert Nahas of the Air Quality Research Group. Ground-based data were obtained from US EPA and North Carolina Department of Environmental Quality. And lastly, I'd like to acknowledge Korean Society of Soil Science and Fertilizer for offering me this opportunity to share our ongoing and exciting research. Thank you very much.
Okay, I'm going to invite the next speaker from Germany, Dr. Andrea Poser. The title is Impact of Agricultural Emission Reductions on Fine Particle Matter and Public Health. Okay, let's play on.
So, hi, good morning, everyone. I'm Andrea Poser, and with my colleague Alexander Tsimpidis, Vlasis Karidis, Alexander Demey, and Jos Lelyveld, we're going to talk about impact of agriculture emission reduction on fine particulate matter and public health. For that one, I thanks again the Korean Society of Soil Science and Fertilizer for inviting me to this international symposium. So, the motivation of this work comes from a paper that was published in 2015 by Jos Lelyveld, where actually he was describing, so to say, the causes of mortality. So which emissions are more important for human health? So actually, which emissions do have the highest impact on fine particulate and therefore on air quality and on human health? And you can see for different regions, like for example, the natural one, which is mostly dust, that has a very big impact on the dust belts. And of course, we have that. We have industrial, so energy production, industry. But what is important is that there's a lot of, let's say, green area, which seems to be like it's here considered as rest, but it could be considered as, let's say, agricultural sources. So Bauer et al. In 2016 published a nice paper showing what the importance of agricultural emissions on PM 2.5. And Lee et al. Shows also that human health is strongly dependent on the ammonia emissions. So actually the idea is like, okay, well, we can just simply connect the pieces of the puzzles, showing actually the impact that we have agricultural emissions on PM 2.5, and in turn, what is the impact of PM 2.5 on human health. And as agricultural emissions is almost entirely, let's say, our anthropogenic emission of ammonia, that goes well along together, showing that actually the human health is strongly depends on the ammonia emissions. For that reason, we just made a numerical model, and we wanted to have with a well-defined numerical model simulation, we have like 4 simulations where we have standard simulation. What would happen if we reduce the ammonia emissions by 50%, by 75%, and by 100%? Therefore, we just decided to have 4 simulations with different, let's say, hypothetical reduction of ammonia and what would happen in the model. And we also defined like 4 regions of interest, which we will discuss later in the results. One is the North America, one is Europe, one is South Asia, and the last one, the red one, is East Asia, which includes, of course, Korea and Japan as well. All the work in here has been performed with the EMAC model. EMAC model is an acronym for ECAM5 MESI for atmospheric chemistry. It's an Earth system model, and you can find a lot of information on this website, www.mesi-interface.org. And it has some peculiar characteristics. So first of all, this model has been, the base model, the general circulation model, has been developed from Hamburg, from the Max Planck Institute for Meteorology in Hamburg, and it's called the ECAM5 model. While the chemistry submodels, which have, so to say, deals with the chemistry in the atmosphere, have been developed with a consortium of institutes. And this consortium developed, so to say, the so-called MESI, so the modular Earth submodel system. Therefore, all this MESI system takes care not only on the interface, but also, of course, for the entire chemicals. So from emissions to chemical interaction to wet and dry depositions and much more, of course. We have different partners that goes from the German Space Agency to, for example, the University of Hamburg, of course, and obviously the Max Planck Institute for Chemistry. So let's check about the emissions. So agricultural emissions do not only emit ammonia, of course, there are different species. Nevertheless, one just should keep in mind that only 5% of black and organic carbon of the black and global organic carbon emissions are from the agricultural sector. So quite low values. At the same time, NOx and SO2, so nitrogen oxides and sulfur dioxide, they have different sources, and agriculture is less than 2% of the global sources of those two tracers. It's roughly 5% of the global carbon monoxide emissions. So we can see that actually agricultural emissions, although it's not purely emitting, it's not responsible for only ammonia emission, the contribution to the other species is almost negligible. Agriculture, on the other side, it's responsible for 70% of the total ammonia emissions, and in principle is responsible for practically the totality of the anthropogenic ammonia emissions. So actually, whenever we talk about ammonia emissions, we normally refer to agricultural emissions, as ammonia emissions from other sources like diesel traffic is there, but it's quite low compared to the from the agricultural sectors. Here on the lower side, I have figures of, let's say, the ammonia emissions worldwide. And you see there are like some places which are, of course, most important, like Europe has quite strong emitters, but of course, Southern Asia and East Asia, they're strong emitters of ammonia, so due to agricultural emissions. So, first of all, we need to check how is the model compared with the observations. And here on the top, we have the observed fine fraction at 35% humidity, and which is almost considered dry, and the model dry mass of 5. And as you can see, actually, we have quite a reasonable agreement spatially. So the patterns are really similar, although we can see that in some cases we have some underestimations, and in a few cases we have overestimations. So the top is like a satellite observational data set. And again, in the bottom is the model results. Values go pseudo-logarithmic scale from 1 to 100. If we make a more detailed comparison based on the stations, the regions that we were discussing before, where we have North America, Europe, South Asia, and East Asia's red, and black is the overall, so to say, the rest of the world, which includes South America and Africa. We can see that actually we have an overestimations on the rest of the world, which is probably due to, let's say, this dust belt, which is normally overestimating. As you see, the reddish color is a bit higher, rest of the world. While, for example, for South Asia and East Asia, the agreement is much better. But we have a sort of underestimation in Europe, as we can see here in the figures. So making a bit of statistics, it comes out that actually the model average and observational average are the model is of course lower in Europe than the observations, and North America is slightly lower, while in South Asia and East Asia we're just quite comparable with and especially in South Asia we have quite reasonable agreement. The PF2 represents the number of points of let's say grid points are within a factor of 2 to the observations. And we see that's 95%, 80%, or 95%. So normally we have higher than 81% in the regions that we are, 80% in the regions that we are interested into. While outside, where there's also the population is much lower than these 4 regions, the agreement is not so good. So 25% of the points are outside the factor of 2. Again, we can just have a comparison with for the components, and here, of course, we have sulfate, ammonium, sulfate, nitrate, and ammonium. On the top, sulfate, and center is nitrate, and on the bottom, ammonium. And we can see that actually the overlaid, there's like the model is the continuous fixtures, colors in the background, while the dots represent and despite the fact that on the East Asian Europe we have quite sparse observational data sets, the agreement I would say is quite satisfactory also for the components. That is important because ammonia of course has different behavior and non-linear behavior with the different sulfate and nitrate components. Again, some statistics on the evaluation, and we can see that actually we are doing quite a very good, I would say, quite good job for a model of thatch dimensions, where we have only some issues over US with the EPAD data sets, with like 63% of the data sets are only 60%, 63% of the data sets are within a factor of 2. For East Asia, so ENET, we have actually, I would say, quite a good agreement for all of the 3 components except for sulfate, which looks to be quite strongly underestimating. We have to, as well to remember that the measurements are quite sparse. Now we go to the results, and actually we'll just check what means actually to have a 50%, 75%, and 100% removal of the agricultural emissions in terms of PM2.5. And as you can see, this is the reduction in percent, where we have that over Europe, decrease could mean 100% removal of ammonia could be up to, let's say, 50 or even more % reduction in PM2.5. And similarly to the is close with the 40% roughly decrease on the Eastern US. On the other side, the impact of agricultural reduction on the fine particulate over East Asia and South Asia especially, it's quite low. The reason is that actually fine particles over South Asia are also caused by black carbon emissions and as well many other sources which are not really influenced by the ammonia or agricultural emissions. So the contribution of agricultural emissions is much lower. At the same time here on the right side, so this on the East Asia sectors, we have a decrease that could be even up to 20, maximum 30% in some locations, which although not negligible is of course much less than what is from other countries. What is important is as well for the particle pH, where actually we had 50, 75, 100% removal again from top to the bottom. And of course, what is interesting to notice that actually we have, yes, a slight change in pH. This is a change in pH units. And the dark side is 2 pH units. So actually what is important in the East Asia, South Asia regions, although the influence of ammonia emissions or agriculture emissions is quite low in terms of total PM2.5, their contribution on sulfate, nitrate, ammonium components, so and therefore on the acidity, is extremely important. That means that without ammonia, the particles would become extremely acidic, or actually they would have increased their acidity by at least 2 pH units in that regions. For that reason, it is important to notice that actually on the East Asia, this impact is much smaller, which could be like up to, let's say, 1 or even less pH unit. Again, the reason of that, because probably the sulfur and nitrate emissions, it's less important for the fine particles in China than in India regions. Or at least, let's say that the East Asia is more buffered by alkaline components coming from other sources. Regarding public health, we can just anyhow check what it is in terms of populations which is, so to say, avoidable mortality by this reduction of PM2.5. And in this case, we can see that actually with a 50% removal, we can just reduce, and that is in 1,000 people per 100 kilometers. We can see that actually we are reducing more than 400 in different locations, and especially over East China, or say East Asia, sorry, and Central Europe, we can go and save, let's say, more than 400,000 people every 100 square kilometer. The reason of that, of course, is not only the decrease in PM2.5, but also on the population density. To make a bit more in context there, we just calculated entire for the entire region what is to say the mortality that is due to PM2.5. So actually we have for reference that we have that normally we have roughly 270,000 persons per year dying like in over Europe. While if we start reducing, we could abate this mortality quite drastically. So by a total reduction of ammonia emissions, we could almost reduce to 1/4 of the total mortality there. So which is quite a very good result. The same is for North America as total results. So we have a strong increase in emissions as relative numbers. Nevertheless, for South Asia and East Asia, the numbers are slightly different for the simple reason that for South Asia, as we said, the PM2.5 is not strongly influenced by the emissions of agricultural emissions, and therefore the reduction is lower. While for East Asia, although one would say, well, the relative changes is not a lot, nevertheless, this is comparable to the European change in absolute terms due to the higher population concentration. So worldwide, we have somehow a quite reasonable decrease. That's as the conclusion. So reducing agricultural emission would cause a reduction of PM2.5 as large as 34% in Europe and 70% in North America. There is, as we said, no significant effects in South Asia, while the relative small change in East Asia. is importantly that the particles become more acidic, especially in South Asia, where the increase of 1.5 pH units, so a decrease of more than 1.5 pH units, so the particles become more acids. So the regulation of ammoniums offer cost-effective control of policy of PM2.5, and that's something that we should think about. Importantly, reducing agricultural emissions by 50%, the mortality attributable to PM2.5 would be reduced by roughly 250,000 people worldwide and more than 100,000 people per year in East Asia. So, well, let's say we will have a decrease of 8%, which is anyhow quite important in terms of absolute numbers. Importantly, there is a strong non-linearity which plays a role in the health impact of PM2.5. So that's why we need to have probably policy action aimed at controlling ammonia emissions. And for that one, I would like to point out this outlook that these results likely to be a lower estimates. In fact, in the last year, and still under debate, came out a new impact factor, function that calculates the mortality due to PM2.5. This impact function is also including data from East Asia. And as you can see, although the curve that we were using before, which were using data up to 35 microgram per cubic meter, and the hazard ratio due to this PM2.5 is quite flatline, while now it's almost common acknowledgement that is more steep. Here we included data up to 85 microgram per cubic meter. As a result, of course, our data implies that when a reduction of PM2.5 will have a much stronger reduction in mortality. That's why our results are somehow considered to be a lower estimate in terms of health and human life saved by reduction in ammonia emissions. The most important questions probably for these audiences is a strong reduction feasible? Well, sustainable should be sustainable between 20 to 90%, and depending on the emission process. For example, slurry acidification changes slurry applications, replacing urea with ammonium nitrate. However, the cost could increase exponentially for reduction above 25%. That's why it's important to have a coherent reduction of all pollutants and not only ammonia, and therefore agriculture emissions should be reduced but should not be stopping from all other emission sources to be reduced as well. And for that one, I thank you for your attention.
Okay, let's move on to the next speaker. The next speaker is from China, Professor Baozing Wu. The title is Societal Benefits of Having Agricultural Ammonia Emission in China Far Exceed the Abatement Cost. Okay, then let's move on.
Hello everyone, I'm Bao Jinggu from Zhejiang University, China. It's my honor to share our recent work with you here. This study mainly focuses on ammonia abatement in China with consideration of their implementation costs and benefit. And we found that the societal benefits far exceed the abatement cost if we reduced half of agricultural ammonia emission in China. Ammonia is an important precursor of PM2.5 that severely damages human health. Furthermore, these ammonium particles can deposit to land and water, leading to soil acidification, eutrophication, and biodiversity loss. Control ammonia emission has become a key strategy to maintain environmental and human health. Globally, we emit about 60 teragrams of ammonium nitrogen each year, of which China contributes over one-fifth, the largest emitter of ammonia worldwide. Other than some hotspots of ammonia emission from wildfires in Africa, majority of ammonia emission is from agricultural sources, especially for China. Therefore, reducing agricultural ammonia emission has become important with global significance. European Union has started to control ammonia emission 2 decades ago. The serious assessment on ammonia mitigation potential, including the national emission ceilings and their abatement costs and benefits, have been conducted. However, these abatement measures and the cost-benefit results cannot be directly adopted by China given the differences in technologies, labor, material costs, and agricultural features and others. Currently, countries and regions finish ammonia abatement analysis mainly from the European Union, with a mitigation potential around 20 to 40%, and the unit cost at several US$ per kilogram ammonia nitrogen. If we sum up this abatement cost on national level, the total cost can be up to $40 billion in the European Union, implying the difficulty to reduce ammonia emission. We have to be smart on ammonia abatement. Otherwise, it would be an impossible mission with such a high implementation cost. How the numbers should be in China is still unknown. To quantify the cost-benefit of ammonia abatement in China, we built an integrated ammonia assessment framework. We first conducted ammonia inventory by compiling data from literatures, remote sensing, and measurements into the chance model. Then we apply Gains model for the abatement cost and benefit analysis. Third, with considering the farm-scale survey, we finally project the future changes of ammonia under different scenarios. We identified 6 feasible ammonia abatement options in crop production, such as using enhanced efficiency fertilizers that can reduce 40 to 60% ammonia emission. Other measures including deep placement, reducing fertilizer use, change the irrigation, and so on. Basically, these measures focus on the 4 R's stewardship on fertilization. For ammonia emission from livestock, we choose measures along the whole production chain, from feeding to housing to manure storage to treatment and application. These measures have very different mitigation potential, which can range from 10 to 90%. Once we have these different measures, they were combined considering their interaction to estimate the total mitigation potential for each crop species. Different crops have different combinations due to their special features, such as maize deep placement is used, while for turfs, drip fertigation may be better. Under this medication combination, we can reduce around half of ammonia emission from cropland, with the steppe food have the largest potential to reduce ammonia emission, followed by vegetables and fruits. The unit cost to reduce 1 kilogram ammonia nitrogen range from $1 to $3. Similar combination processes are also applied to livestock along the nutrient flow chain. I will not read all this, just quickly show you these measures and their combinations. Compared to cropland, the mitigation potential of ammonia emission from livestock is similar, around 50%, but the unit abatement cost is a little bit higher given the difficulty to manage manure for ammonia reduction. If we put cropland and livestock together, we can find that Chinese agriculture has an overall around 50% of ammonia mitigation potential, and livestock has a slightly larger contribution than that of cropland. The unit cost is around $1 to $2 per kilo ammonia and nitrogen, with a total cost at $6 to $11 billion. Pig and poultry production contribute the largest share of ammonia mitigation. If we put all these measures together based on their unit cost, then we'll have a Chinese marginal abatement cost curve. This curve is very important for the guideline of ammonia abatement, which is varied across countries. Based on this curve, China can achieve 1/3 of its ammonia mitigation without any net cost. It's not saying we don't need investment for ammonia abatement, but suggests that the abatement benefit is larger than the cost, such as the profit of fertilizer saving is more than the implementation cost. However, with the increase of a total ammonia reduction amount, the unit cost increase dramatically. These measures can be divided into three major pathways, including nitrogen use efficiency, we call NUE, and the nitrogen recycle, we call REC, and optimizing human dietary structure, we call DIET, DIET. The first two are technical measures, and the last one is non-technical measures, which can further promote ammonia reduction at about 10%. Results show that we cannot achieve half of ammonia emission with only one suite of measures, and we have to combine all these three measures together, including NUE, recycle, and DIET. Then we can have about 60 reduction potential overall, higher than the total national target, around 40 reduction potential of ammonia emission in hotspot regions such as the North China Plain, where it suffers severe PM2.5 pollution. We further calculate the societal benefit of ammonia abatement, including human health, ecosystem benefit, and the greenhouse gas reduction. If we put all these benefits together, then ammonia abatement can bring much more benefit than its implementation cost. Even we include the increase of acid rain damage, it suggests that China can have much more societal benefit of ammonia abatement, although farmers may need invest more to control ammonia emission, and the whole society should pay for this cost given the essential food supply from agriculture and the whole societal benefit from the ammonia mitigation. Thank you very much. And this work has just been published in Nature Communication. If you have any interest of this work, please go to Nature Communication for the whole paper. Thank you.
Okay, I want to invite next speaker from Japan, Professor Genki Katata. The title is Law of Aggression, a case study whether Japan's lake basin influenced by agricultural ammonia species. Let's play on. Okay.
Hello everyone, I'm Genki Katata, who is a Session 2 keynote speaker. Thank you very much for invitation from Korean Society of Soil Science. So let's start my presentation from next slide. So what can you imagine from this photo? A large car with dust or small particles? No, these are all agricultural fertilizers. Fertilizers are very important to feed a great number of population by producing a large number of crops. So this is a great benefit for the humans, but still there is risks or costs. So the risk of agricultural fertilizers is the cost of nitrogen pollution. Reactive nitrogen is a species of nitrogens easily reactive in the environment. The ammonia is one example of this, mainly comes from agricultural fertilizers. So this graph shows the cost of European Union for each gas species and reactive nitrogen in water. There is a variable for human health, ecosystems, and climate in the impacts on environmental impacts. We can see the high values of ammonia in terms of human health effect by formulating particulate matter such as PM2.5. So that's why it is very important to know what is an agricultural emission source of atmosphere. This is one of the examples from our university. Beef cattle house with nature, manure, and compost, for example. All of them are the agricultural emission source from livestock. So what happens once ammonia emitted to the air? They dispersed in the atmosphere to form the aerosols, such as PM2.5. A part of them can be absorbed by clouds to make a rainfall, like wet deposition to the land of the nitrogen. A part of them still have a dry depositions from air to the lake. Sometimes air-water gas exchanges also happens. So both are deposition processes which have the nutrient pollutions to the lake ecosystems. For example, algal formation. So this is one of the risks. We should know how to form it in the lake basin scale. So this figure shows a large variety in the ammonia concentration in the world. This is the result from the satellite recently published in the atmospheric chemistry and physics. As you see here, you can see a very large concentrations around the north of India. For example, there's also kind of the hotspots in China and Africa and South America, for example. Let's see much more closer scale in the country scale, for example. This is China. There is also the satellite measurement as represented as the green shaded areas. There are large hotspots around here in China. We can still confirm it by the filter sampling as represented by large circles with red or purple here. So this photo shows this is quite heterogeneous in terms of the ammonia emission concentrations, which makes difficult to understand how to mitigate this kind of agricultural emission sources in the world. So this slide summarizes the motivations and objectives. We currently have less monitoring networks for ammonia concentration in lake basin scale. Also, we don't know a dominant factor determining the spatial variation of ammonia concentration in this scale. Therefore, we did some 60 monthly multi-point observations around the shallow eutrophic lake basin in Japan. The data is analyzed with meteorological variables and emission inventory. And finally, implications for ammonia source management in the lake basin are discussed. So this is a study area, namely Lake Kasumigaura in Japan here. And the crossed point shows the ammonia sampling, a square shows the weather station, and the shaded area shows the emission inventory of ammonia. This is the Lake Kasumigaura as represented as the shaded area and the high emission area of the north. There are 36 number in total or for sampling points, including 80 number of monthly monitoring and the other 80 number of intensive seasonal monitoring for summer and winter. Okay, let's show the results of this result from next slide. This is a seasonal change of ammonia. This is a rural, forest, farmland, and lake in the order. The ammonia concentration is here with the changes of monthly sampling from 2018. As you see here, for example, in rural sites, we can see a large variety in the concentration. But still we can see this red line as the mean values of all of the stations. So seasonal change can be discussed from this figure, and we can see interesting feature from farmland and lakes. What is important? What is interesting? This is the wintertime increases here, and in summertime, the concentration was not so large. So this is similar to in the lake categories areas. And surprisingly, actually over the lake, there is large values of ammonia concentration observed during the winter time, as compared with other categories such as rural and forest. Why this is interesting and important? We can compare the emission inventory with ammonia concentration. This graph shows the monthly changes in air temperature and emission inventory, which is from this dataset. This graph shows usually the temperature is increased during the summer, as you already know that. And the inventory also increased during the summer due to the temperature-driven vaporization process modeled in the inventory. But this is just model. In fact, if you see the ammonia concentration average for each land use, you can see this kind of typical change of maximum values during the winter time, as we already see from the last slide. So what happens here? We can explain from this phenomenon from this temperature-driven vaporization. Many of results of ammonia concentrations in the world shows quite similar to the inventory changes, such as the temperature-driven vaporization. But our study is not. To know the dominant factors determining ammonia concentrations, we compared with the meteorological variables with ammonia concentration at all stations. This is the air temperature and wind speed, wind direction, and precipitation. As you can see, for air temperature, wind speed, and precipitation, there are no so clear correlation between the ammonia concentration. However, we can see the very high values of ammonia concentration for northern winds. Also, we can still a very weak correlation with the wind speed, which may show the importance of advection of ammonia concentration from high place to low place. We try to confirm this hypothesis by spatial ammonia distributions in season. This figure shows the result of summer. This graph shows the winter for intensive monitoring results for 36 points. The circle shows the ammonia concentration measurement, and the vector shows the wind velocity and direction. As you can see, there is the highest emission area, also the highest concentration values observed. And this in summer, actually the southern wind is dominant, but winter time this is opposite. Northern wind is dominant. And then we can see the high values of ammonia concentration just above the lake or just north of the lake. Even in the center of the lake, this value should be a little bit higher than the summertime. This is much clearer if you can see the concentration difference between the winter time and summertime. As shown in the red circle, this is a quite high concentration difference in the area of north of Kasumigaura Lake. There's also the positive values over the lake too. So this is quite important to know that how amount of deposition of nitrogen due to this concentration difference. Then we did preliminary estimation of annual ammonia deposition. We used the inflation method as represented by this equation, and the values of observations was used to the concentration and literature values of dry deposition. So this figure shows the temporal change in the dry deposition estimation results and also the wet deposition observed values by the land. The final result of annual basis was that dry deposition was 9.1 and wet deposition was 5.6 kg per hectare per year. So both are actually almost 15 kg to the lake, which may be important to the nitrogen input to the lake ecosystem. So let's summary of this kind of processes in this figure. Usually we know the agricultural sources, which is an emitter of ammonia to the air, particularly around the livestock areas here. Usually all of those should be deposited around here, but wintertime there's actually a monsoon circulation from the north to the south, and it brings some high ammonia concentrations over the lake Kasumigaura and then deposit. So this could interact with the lake ecosystem at the lake surface. As shown in these photos from the satellite, this shows the cyanobacterial bloom during the summertime. So this is quite different seasons, but still we still think about the nutrient input is quite high by the dry deposition into the lake during the winter time. So we should think about the management of lake ecosystem based on this kind of role of advection. So in conclusion, we have a new findings as nitrogen concentration was higher in winter than the summer. Seasonal advection from the agricultural sources should have a role in lake basin scale. And finally, dry deposition of ammonia could have an impact as nitrogen input to the lake. The rest of the question is, for example, that is the seasonal pattern of ammonia deposition that matter for lake existence. This is a kind of interesting topic should be discussed in this conference in terms of the particle formation in the atmosphere from the ammonia. Thank you so much for your attention. This is our latest paper from this presentation with a great number of contributors in Japan.
Okay, I'm going to move on to the next speaker. He is the last speaker in this session. I'm going to invite Nanti Burman from Australia. I think he is watching this program in Australia at the moment. He just emailed me. I must say hello to Nanti. Okay, his topic is source, health impact and mitigation of particulate matter disposal in agriculture. Let's meet Nanti.
Good morning. My name is Nanti Bolan. Firstly, I would like to thank the organizers of this conference for inviting me to give this presentation. The title of my presentation is Sources, Health Impacts, and Mitigation of Particulate Matter Exposure in Agriculture. Particulate matter in agriculture is a burning issue. It is a burning matter which requires some urgent action. This is the outline of my presentation. Firstly, I shall give some examples of the sources of particulate matter in agriculture. Then I shall explain the characteristics of particulate matter and the impact of these particulate matter in agriculture. Finally, I shall discuss the prevention measures of particulate matter exposure in agriculture. Particulate matter includes a mixture of solid particles and liquid droplets found in the air. Particle pollution includes PM10, which are inhalable particles with diameter less than 10 micrometer. The other group is PM2.5, fine inhalable particles which are respirable with diameter less than 2.5 micrometer. This figure gives the relative sizes of particulate matter in comparison to human hair and beach sand. For example, the size of red blood cells is around 8 micrometer, which means the finer particulate matter, which is PM2.5, can travel through blood vessels. Now, I shall talk about the sources of particulate matter in agriculture. Sources of particulate matter exposure in agriculture include geogenic or natural sources. A typical example is dust from soil. The other group is anthropogenic sources introduced by human activities in agriculture. Some of the examples include ammonium nitrate, dust, smoke, or soot from cultivation, harvesting, and stubble burning. Now, this flow diagram gives the various routes of particulate matter release in agriculture that include plant production system and animal production system. Ammonium nitrate is an important secondary aerosol particulate matter in agriculture, and it is a major source of this aerosol particulate matter. It is formed when nitrogen oxides produced by vehicles combine with ammonia, which is released from farms that use ammonium-based fertilizers and also that produces animal manures. As you can see from the bar diagram, agriculture is a major source of ammonia particulate matter in the environment. Cultivation is a major source of particulate matter released from agriculture. This bar diagram gives particulate matter released from various agricultural activities, including cultivation. For example, soil cultivation in India produces large volumes of particulate matter dust, which is causing severe health implications to human and animals. Also, it causes transboundary visibility impairment, what is known as smog or haze. Harvesting and haymaking also contribute to particulate matter release. Combined harvesting using machineries releases large volume of crop dust particulate matter. This bar diagram compares particulate matter concentration in wheat harvesting and corn harvesting, haymaking, and baling. All contributes to particulate matter release in harvesting. Animal production also contributes to particulate matter release in agriculture, which is resulting mainly from feed and manure management. This table gives particulate matter emission from various animal production systems in a number of European Union countries. On a unit mass basis, poultry farming produces greater amount of particulate matter than cattle and pig farming systems, mainly due to the handling of feed and manure in poultry production. Now, I'm going to briefly introduce some of the characteristics of particulate matter in agriculture. Particulate matter from agriculture composed of inorganic and organic dust, gases, and chemicals. This table gives the various components of particulate matter released from agriculture. For example, the inorganic soil dust produced during cultivation contains a number of elements including toxic heavy metals. Similarly, the organic crop dust produced during machine harvesting contain pesticide and nutrient elements. Particulate matter from agriculture also composed of microorganisms including bacteria and fungi. This bar diagram gives the distribution of bacterial and fungal species in particulate matter exposure from agriculture. These are mainly derived from animal production, resulting from manure handling and spreading of these manures. Now, I shall talk about the impacts of particulate matter exposure in agriculture. Particulate matter causes both environmental and health impacts. If you look at the health impacts, it is the finer particulate matter, including PM2.5, pose the greatest problem because they can get deep into our lungs and also get into the bloodstream. Exposure to such fine particulate matter can lead to premature death in people with heart and lung diseases, aggravated asthma and decreased lung function, increased respiration system that include irritation of the airways and difficulty in breathing. Particulate matter causes environmental damage because particles can be carried over long distances by wind and then settle on ground or water, and thereby resulting in acidification of lakes and streams, nutrient enrichment, that is eutrophication of coastal waters and large river basins, depleting the nutrients in the soil, affecting the diversity of the ecosystem, contributing to acid rain effect. Particulate matter also causes visibility impairment. Fine particles, PM2.5, are the main cause of reduced visibility. It also causes material damage. Particulate matter can stain and damage stone and other materials, including culturally important objects such as statues and monuments. A typical example is the deterioration of one of the wonders of the world, that is the Great Taj Mahal of India. Finally, I shall discuss about the prevention measures for particulate matter exposure in agriculture. Particulate matter release can be prevented or reduced by improved farm operations such as no-till farming, reduced stubble burning, and manure management that can help to prevent particulate matter pollution. Regular use of personal protective equipment such as mask and head cover will help to reduce health impact of particulate matter. Construction of windbreaks in farms can reduce the transboundary spread of particulate matter. Now some of the conclusions. Agricultural field operation including soil cultivation, planting, fertilizer and pesticide application, harvesting, and post-harvest processes release particulate matter. Animal production system causes particulate matter production from feed and bedding material and manure management. Particulate matter from agriculture is contaminated with heavy metals, organic chemicals, including pesticide and microbes. particulate matter causes health and environmental impact in addition to smog or haze, which is visibility impairment. Improved farming operations such as no-till farming, reduced stubble burning, and improved manure management can prevent particulate matter production. Finally, what is the take-home message? Agriculture operations are an important source of particulate matter exposure. Particulate matter resulting from agricultural operation can cause health and environmental impact. Improved farm operations, including no-till farming, reduced stubble burning, and manure management, can prevent particulate matter exposure and pollution. A number of countries are introducing regulations to reduce particulate matter exposure from agriculture. A typical example is reduced cultivation, reduced stubble burning in India. Finally, I would like to thank our past and present students for undertaking some of the work reported in this presentation. Once again, thank you for inviting me to give this presentation. It is indeed a great honor to give this presentation. Thank you.
Okay, this is the end of the first session. I thank to all 7 speakers, and we will have 10 minutes break. After that, Professor Jimmy Park will take his charge of the second session. Let's see after 10 minutes then. Thank you.
Thank you for attending the second session of the symposium. My name is Juniba from Chungung National University. The first speaker of the session is Dr. Kamal Adhikari from New Zealand. The title of the presentation is Mitigation Potential of Urease Inhibitory Compounds in Reducing Ammonia Emissions from Cattle Urine in Pasture Soils.
Hello everyone, welcome to my presentation. At first, I would like to thank the Korean Society of Soil Science and Fertilizer for inviting me as a keynote speaker in an international symposium on production and mitigation of fine particulate matter in agriculture. Today, I'm going to talk about mitigation potential of urease inhibitory compounds in reducing ammonia emissions from cattle urine in pasture soils. Let's start with a little bit of background. Globally, agriculture sector is responsible for most ammonia emissions, and livestock production systems contribute to most of global agricultural ammonia emissions. In intensively managed graze pastoral systems, urine deposited by livestock during grazing is the key source of ammonia emissions. This urine covers about 20 to 30% of pasture area annually and contain the equivalent addition of 200 to 2000 kg nitrogen per hectare. Urine contains about 80% urea N, and on average 12% of N deposited is emitted as ammonia, ranging from 2 up to 66% of N deposited depending on soil and climatic conditions. These emissions represent both economic and environmental losses. For example, in New Zealand, the ammonia emitted from dairy cattle excreta is equivalent to NZ $94 million per year, and urine accounts 60 to 70% of it. Similarly, emitted ammonia acts as a secondary source of greenhouse gas nitrous oxide and secondary aerosols and particulate matter, which are detrimental to human and animal health. The ammonia redeposited into the ecosystem causes eutrophication of aquatic bodies and acidification of soils. Several approaches such as irrigation management and use of urease inhibitors have been used to reduce ammonia emissions from cattle urine patches. However, irrigation management is not feasible in non-irrigated farms, and in some cases, irrigation can move urine N below the root zone, making it unavailable to plant and susceptible to leaching. Several urease inhibitors have been patented to reduce ammonia emissions. However, only two of them, N-butyl thiphosphoric triamide (NBTPT), which is traded as Agro-10, and our recently introduced urease inhibitors N,2-nitrophenyl phosphoric triamide (2-NPT), have shown effectiveness in reducing ammonia emissions from cattle urine patches. Both of these inhibitors are specific in nature. They inhibit the activity of the enzyme urease, which is responsible for urea hydrolysis, the first step of ammonia emission process. This table shows the effectiveness of inhibitors in reducing ammonia emissions from cattle urine patches. On average, Agro-10 and 2-NPT reduced ammonia emissions by 34 and 20% respectively. However, the reduction achieved by 2-NPT was based on only two studies. In studies with Agro-10, for majority of studies, Agro-10 was either mixed with urine before application or applied before urine, which is unlikely to happen in real grazing scenario. In practice, there is always a delay between the urine deposition and inhibitor applications. Few recent studies have assessed the effect of inhibitors applied after urine, and these results suggest that the effectiveness of inhibitor applied after urine depends on soil conditions and timing of inhibitor applications. For example, if you look at the second last row of this table, under dry and warm soil conditions, both inhibitors agrotane and 2-NPT did not reduce ammonia emissions when applied 3 hours after urine. However, under wet and cool soil conditions, both inhibitors reduced ammonia emissions when applied 3 hours after urine. Similarly, under wet and cool soil conditions, the efficacy of inhibitors was greater when applied immediately after urine compared to 3 hours after urine. These results suggest that the effectiveness of inhibitors in reducing ammonia emissions from cattle urine depends on the physical contact between the inhibitor and the urine N. The more physical contact, the more reductions. And the physical contact between the inhibitor and urine N depends on soil conditions such as soil moisture, soil temperature, and timing of inhibitor application when inhibitors were applied after urine. So far, there are no any evidences of negative consequences of inhibitors on pasture production, soil microbial activity, and grazing animals and their products. However, some of the inhibitors applied may be captured by the pasture canopy and enter into the food chain through grazing animals, which is evidenced by discovery of another nitrogen process inhibitor, nitrification inhibitor DCD, in milk in New Zealand as a result of blanket application of DCD in pastures. There is a technology available for mapping and targeted application of inhibitors in urine patches using inhibitors with the use of New Zealand devised machine Spiky, which may reduce the potential entry of inhibitors into the food chain through grazing animals and also reduce the cost associated. In conclusions, urease inhibitors agrotane and 2-NPT are effective in reducing ammonia emissions from urine patches. However, reducing ammonia emissions from urine patches using urease inhibitors requires close contact between the inhibitor and urine. Therefore, future research should focus on ways to optimizing the efficacy of inhibitors, which include determining the factors regulating the effectiveness of urease inhibitors applied after urine. For example, timing and rate of inhibitor application, volume of inhibitor application, and detection and targeted management of urine patches. Similarly, more field studies to assess the fate of inhibitors applied on grazing animals and their products and surrounding environments are needed. In this slide, I have listed the references used for assessing the effect of inhibitors on ammonia emissions used in these presentations. Thank you for your attention.
I'm going to introduce the second speaker of the presentation, Youngjun Kim from Korea University. He will be presenting on development of effective microorganisms for reducing ammonia emission from livestock manure.
Hello, my name is Youngjun Kim in the Department of Food Science and Biotechnology in Korea University. I'll talk about the development of effective microorganisms for reducing ammonia emission from livestock manure. Today's topic will be including the background of research and the screening method and the effectiveness of bacteria in the yeast. Particulate matter can increase the risk of the human health, including the pulmonary inflammation, autonomic dysfunction, and also it can increase the chance of systemic inflammation and oxidative stresses. Actually, the Korea is #1 in the OECD countries in terms of air pollution level, and there is increasing level of particulate matter, and which is classified as a carcinogenic hazardous substances, and it is a direct cause of respiratory diseases. There has been increase in the emission of the ammonia level in the atmosphere, as well as volatile organic compounds, and there is the proportional increase in the ammonia emission and the fine dust. The fine dust, which is caused from ammonia, can cause the direct damage to the human health and many different organs and the tissues. And it is produced from air pollution from different sources, including the livestock. And they directly produce ammonia. And then there are many precursors, which is derived from air pollution sources, can contribute to the ammonia production. And this is the main cause of fine dust, especially fine dust 2.5. And ammonia gas emission into atmosphere is mainly caused by agricultural products. And livestock manure is about 90% of agricultural product. The trend is same in the European countries. So livestock manure management sector accounts for a large proportion of ammonia emission, and it is very important to control the ammonia emission from livestock manure, which is the main purpose of this study. Many livestock, including Hanu and other type of cattle and pigs and hens, they produce lots of manure by composting, and ammonia can be produced during the composting. And ammonia can be emitted from the livestock manure, and it is produced from urea and other nitrogen compounds by urea hydrolysis as well as deamination. And if you have high ammonia production, then pH is increased, and also it is one of the reasons we have gas emission, ammonia gas emission. And we have many reduction methods, physical way and chemical way, but we think it is more efficient to use biological method using effective microorganisms because we don't have to have facility and there's no secondary pollution risk. So in this study, we focused on the development of effective microorganisms. First, we screened some bacteria and the yeast based on 3 different criteria. In this study, we looked at the pH decrease and direct ammonia remover, at the same time the urease activity, which is catalyzing the ammonia production from urea. So we selected many strains. This is part of our screening studies, and we give some score at different criteria. If you have 80% higher than 80% inhibition in urease activity, or 30%, more than 30% inhibition in yeast, we selected. And if the removal rate ammonia is higher than 10%, we give the positive score. And if we looked at the delta pH, just a decrease in pH is more than 1, then we give the positive point. So we finally selected 3 strains, 2 from bacteria, 1 is the yeast. And these 2 strains were later identified as Pediococcus actylacticea. So we checked the survival rate of these bugs in the manure by measuring the DNA depending on the proportion of inoculum. And we found the direct increase depending on the amount of inoculum. The higher the initial inoculum, higher the DNA contents. But that was not the case higher than 8% in case of 12-3. So we found 8% was optimal inoculum, and higher than 2%, we started to look at the significant increase in the survival. So we choose 2 different conditions for further 2 concentrations for the further study. So we looked at pH decrease with the 2% and 8% with the 2 different strains and in 2 different atmospheric conditions, aerobic and anaerobic. After 24 hours, we found a significant decrease, especially in the aerobic conditions compared to the control with both strains, which is about like more than 0.6 in just 1 day. So these 2 strains can contribute to the decrease in pH, and hopefully it can decrease ammonia production. At the same time, we looked at the inhibition of this strain inoculum against the survivor of hyperammonia producing bacteria, which is Clostridium aminophyllum and Proteus mirabilis. These strains exist in the manure. They produce ammonia. At the same time, they are pathogenic. So it's worthwhile to control these 2 bacteria. And we found these 2 strains can inhibit the survival of these 2 bacteria in the manure, and especially in the aerobic conditions. So we looked at the effect of these strains both in aerobic and anaerobic conditions, because during the composting there could be some aerobic condition in the surface, but mostly in the manure it is anaerobic conditions. So it is important to look at those 2 different conditions with the and we directly measure the ammonia emission, and we found significant decrease in the ammonia gas accumulation in our system, which is we culture this bacteria with the 100 gram of livestock manure, and after 35 days we found significant decrease in the ammonia emission. We added up all the ammonia production during the 5 weeks, and with the 12-3 we found most effective inhibition in terms of direct ammonia production, which is about 40% and much higher than IL-12-1, which is 25% reduction. We also looked at the total nitrogen is decreased in the control. Also, the urea is decreased, which is 22% and 62% respectively. And this reduction was lower with the two inoculum, which is about 15% and 10% of total nitrogen, and urea was maintained more than the control, which is about 50% and 45% in these two bacteria we tested. So these two strain inoculum suppressed the urea hydrolysis of manure. As a conclusion, we found these two bacteria can decrease the pH during their composting. At the same time, they can inhibit the growth of ammonia-producing bacteria. So in both ways, it can control the ammonia production during the composting. We also looked at the effect of yeast. We chose two strains, which is Saccharomyces boulardii and the Saccharomyces cerevisiae as a control. So we tested the survival rate of these two yeasts in the manure. We were very suspicious about the survival of these two strains in the manure, but surprisingly, they were surviving. There's no big difference between these two atmospheric conditions, and there's no big difference in the survival rate between these two strains. But this study showed us possibility for these strains can be dominant in the livestock manure. So we inoculated, and after 24 hours, we checked the pH, and which was decreasing in the boulardii compared to the control, and not as much as cerevisiae. And the rate of decrease was more prominent in the anaerobic conditions. So which indicate us that it can decrease the pH during the composting. At the same time, we looked at the inhibition rate against these two hyperammonia producing bacteria, like we did in the bacterial studies. We found the boulardii strain can decrease the survival of these two strains only in aerobic conditions. Okay, and the rate of decrease, rate of the inhibition of these two strains was more significant in the aerobic conditions. Total ammonia gas emission was also decreased in case of Saccharomyces boulardii inoculation after 35 days compared to the Saccharomyces cerevisiae, which is about 25% of reduction. And we also looked at decrease in the total nitrogen reduction compared to the control, and also urea reductions, which means they did not change the urea into the ammonia when we inoculate these bacteria. But that was not the case with the control strain, Cerevisiae. So we found the same effect, not same degree with the bacterial studies. And we try to look at how we can increase the survival of these strains in the system. And we gave the heat stress. Actually, during the composting, the temperature is increased. So it is important to maintain the survival of these strains during the composting. So we try to increase the resistance against the high temperature condition by adding trehalose, which was previously screened. And it can decrease the ROS production, actually, and we found endogenous hydrogen peroxide level was dramatically decreased when we treat with the trehalose, when we grow this yeast. So we concluded that trehalose application can increase the heat resistance of this strain and give the protective mechanism against reactive oxygen species. And we also looked at the effect of trehalose against the survival rate of yeast. And we studied some mechanism. We tested the expression level of caspase, of yeast caspase, and we found its caspase activity was increased by heat stress, and which was neutralized by adding trehalose. So eventually they decreased the cell death of these yeast strains, which means trehalose addition can give the protective effect against the yeast survival. Summary. So we found a similar result with the bacteria, and we found decrease in the pH. We found the inhibition of this hyperammonia producing bacteria by the addition of Saccharomyces boulardii, and that was more enhanced by adding trehalose, which can protect these strains against heat stress and RS stress. So we found the bacterial strains, Pediococcus, and the yeast, Saccharomyces boulardii, can be applied as a part of microorganism, effective microorganisms, which can be applied to the manure during the composting, and they can decrease the ammonia production, and hopefully they can decrease the fine dust at the end. So it should be more optimized to have the best condition for the application, but this study could contribute to the studies of development of the effective microorganisms. And this study was supported by National Institute of Agricultural Sciences in the cooperative research program. And I thank many colleagues, especially the Sunil Kim, who was the major performer of these studies, and he is going to graduate with this the result, and other many colleagues. Thank you very much.
The next presentation is application of humic action solution reduce the possibility of ammonia emission by influencing activities of microorganisms related to nitrogen cycle in soils with special reference to tea cultivation in India, which will be presented by Dr. Prahat Pramanik from North Bengal Regional R&D Center, India.
Greetings from India. With the wishing for good health of everyone, I am starting my presentation. Today I am going to discuss about how application of humic acid solution can reduce the possibility of ammonia emission from soil by influencing activity of microorganism related to nitrogen cycle. Our reference crop will be tea. I am Dr. Prahat Pramanik from Tea Research Association. India is the second highest tea producing country in the world, and it has three major tea producing regions. Among them, Northeast India is the most important one. This is the largest tea producing territory in the world. Tea Research Association deals with research and development of Northeast India. I am soil scientist of this institute. The average area of tea gardens in Northeast India is 250 hectares. However, they may be extended up to 800 to 900 hectares also. Large amount of chemical fertilizer is annually applied, especially urea and MOP, and this is the pluckable portion of tea. Tea is commercially cultivated for harvesting young tender shoots. Total area under tea cultivation in Northeast India is 6.37 lakh hectares, and it produces 1,03,038 million kg tea annually. Unlike other crops, in case of tea, a dose of urea is fixed on the basis of productivity in last pruning cycle along with soil nitrogen content. So if we consider the large area of tea cultivation in India and its huge productivity, a huge amount of urea is annually applied in tea gardens. For a section of the tea which produces 2000 to 2500 kg metric ton tea, 100 kg nitrogen in the form of urea is annually applied in 2 to 3 doses, splits depending on soil and climatic conditions. When urea is applied in soil, through nitrification it produces nitrate ions in soil. There are two major pathways. However, among them urease mediated pathway is preferred due to its lower T half. During this process, ammonia is generated as the intermediate compound. Those ammonia emits from soil and reacts with volatile organic carbon compounds, nitrogen oxides and sulfur dioxide to form finer particulate materials PM2.5. Those finer particulate materials are harmful to human health as they can be deposited into human lungs. In last 70 years, global emission of ammonia is doubled from 23 Tg per year to 60 Tg per year. Our cultivation process is largely depends on urea application. Our concept is that urea application will enhance the crop productivity. However, application of excess amount of nitrogenous fertilizer can turn into gaseous ammonia, and that is harmful to environment. It was estimated that 50% reduction in agricultural ammonia emission may reduce death up to 2 lakhs deaths per year across the world. Hence, it is very important to enhance the nitrogen use efficiency in soil, and to reduce that will reduce the ammonia emission from the agricultural soil. Our focus was on this part of nitrification process. We hypothesized that if we can enhance the rate of nitrification, that is conversion from ammonium ion to nitrate ion, then the rate of ammonia emission from the soil might be reduced. Hence, we conceived one experiment to enhance the nitrogen use efficiency in soil by applying humic acid solutions. We applied one treatment was 100 kg nitrogen per hectare, that is the recommended dose, and thereafter we gradually reduced the dose of urea and applied 500 liter per hectare basis humic acid solution in soil. This way humic acid solution was applied in soil near the collar of tea bushes, and tea shoots were plucked at 7 days interval. It was observed that tea shoot productivity was dependent on climatic condition. When climatic condition or weather condition is favorable, then productivity was higher, and with decreasing temperature and rainfall, gradually tea productivity was reduced during winter time. Tea shoot yield did not differ significantly among the treatments on a particular day of sampling. However, we collected the yield data for 140 days. When we made summation of that data, the cumulative tea productivity was significantly differed among different treatment. It was observed that tea productivity of recommended nitrogen dose was at par with 75%, even up to of 50% recommended dose of nitrogen application when humic acid was applied in soil. That was a big finding, and we were interested to find out what is the reason behind that one. Hence, we estimated available nitrogen content in soil, and it was observed that nitrogen availability in soil was increased when humic acid was applied in soil. Even only 75% applied, 75% of recommended nitrogen dose applied treatment had shown higher nitrogen availability, especially in the second year when humic acid was applied in soil. The same trend was observed when we evaluated nitrate nitrogen content in soil. There also humic acid treated soil recorded higher nitrogen content, and that recommended chemical urea dose had shown lower nitrate nitrogen content even from as compared to 75% of recommended nitrogen and humic acid treatment. However, that trend was reversed when we compared ammonium nitrogen content. Here we found that recommended that chemical fertilizer dose had shown 100% urea applied treatment had shown highest ammonia content in soil. Hence, we can say that definitely humic acid application had played an important role to convert nitrogen into nitrate form, and that in turn reduced ammonium ion concentration in soil. For further study, we estimated microbial activity in soil, and we found that all the humic acid treated soil had shown higher microbial activity as compared to 100% urea applied treatment. Microbial activity, nitrate, that population of nitrifying bacteria was also increased due to humic acid application, especially in the second year, that 75% urea and humic acid treated soil had shown higher nitrifying bacterial population as compared to 100% urea treated soil. Therefore, we can say that humic acid application definitely alters microbial population in soil, and it boosts microbial activity and worked on especially nitrifying bacterial population to enhance nitrogen availability in soil. Hence, therefore, we can conclude that humic acid application at 10% dilution can enhance the rate of nitrification in tea growing soil. Nitrogen use efficiency was increased during this study. Humic acid application reduced ammonia ion concentration in soil, and higher concentration of nitrate ion and lower ammonium ion concentration in humic acid treated soil mitigated possibility of ammonia emission and formation of PM 2.5 particulates in the atmosphere. Thank you very much for your kind attention. Stay safe.
Before we start the next presentation, I should say sorry for the screen shake. Now we are going to introduce the next presentation. The title is Nitrogen Dynamics on the Switchgrass Seeded or Marginal Lands, which will be presented by Dr. Sandeep Kumar from South Dakota State University, USA.
Myself, Sandeep Kumar, Associate Professor in Department of Agronomy, Horticulture and Plant Science at South Dakota State University. I want to talk about today regarding nitrogen dynamics under switchgrass seeded on marginal lands. To give you a brief overview about the soils and water quality problems, especially in the Midwestern region. We have a huge problem of soil erosion and degrading soil health because of the intensive tillage application, and also land use conversion. A lot of grasslands in this region were converted into croplands, and that created a lot of erosion, and hence the water quality and soil quality degradation. Cattle grazing also on the stream banks without any buffer increases E. coli in streams and create water quality problems. Recreational activities also impacted by water quality, especially in major watershed. And Big Sioux River is the major watershed uh, in South Dakota, and this watershed considered as the most polluted, ranked number 13 in the nation. So these are the few pictures that you can see. This is the intensive tillage field where nutrient sediments they are coming with the rain and going mixing with the streams. And there is no buffers here between the cattle grazing and in the pasture land, and that's creating a huge issue. So I'm not discussing about too much about agricultural land. I want to discuss a little bit of the marginal lands. Those are contributing the major soil health and water quality problems. So these marginal land, these are considered as a low productive lands. They reduce economic return because they have a very limit use for agriculture land, very vulnerable to the erosion and very low crop productivity. Crops, they grow on these lands, but they don't perform well. And the soil health and water quality are the biggest issue on these lands. So perennial grasses such as switchgrass, these are very suitable for these marginal lands. A producer, they use these perennial grasses on these land for a few years, and once the uh, soil health is improved, then they go back to again agriculture land. So I want to talk about the switchgrass primarily on these marginal lands. Switchgrass is a perennial C4 grass with deep root system, suitable for marginal yielding lands and native to North America. And it's very good feeds bioenergy feedstock, and it's also used for a livestock forage, soil stabilization, and wildlife cover. But it needs a nitrogen fertilizer, and we want to make sure we don't over fertilize it or under fertilize it. So optimum nitrogen rate is very important for enhancing the soil health, carbon, and to maintain the water quality. So research question that I want to talk about today: what is the best nitrogen rate for the switchgrass without it negatively impact the environment on the marginal lands, and can switchgrass benefit soils and the environment in the long term? So based on these research questions, my major focus of this talk is to evaluate the impacts of nitrogen rate and landscape position on soils property, nitrate leaching, and N2O fluxes, and to investigate the optimum application of nitrogen rate for increasing the switchgrass biomass production. So experimental site, it's located in uh, north side of US. It's a South Dakota, loamy soils, and the switchgrass was planted in 2008, and it was considered the marginal land, pretty high slope, 15 to 20% slope, and it was very low productivity for the agriculture crops. And about 10 hectare land was marginal land was used for growing the switchgrass. We tested 3 different nitrogen rates: 0 kilogram nitrogen per hectare, medium was 56 kilogram nitrogen per hectare, and high 112 kilogram nitrogen per hectare. And we seeded these switchgrass at 3 landscape positions: shoulder, back slope, and foot slope. So site management, we had 4 application, and you can see here these are the 4 application and the 3 nitrogen rate, and the slope was 2 to 20%. So soils and water samples collected all the way from 2009 to 2012. We're still collecting it, but I'm just showing you data for over like 6-7 years. And we used a lysimeter, suction lysimeters, installed at 100 centimeter depth at 36 positions. So greenhouse gas fluxes were collected using the static chambers, and samples were analyzed using the gas chromatograph. So data showed that soil organic carbon in 2009, when we started the experiment, it was insignificant, and the carbon was about 2.4%. And over the years, the soil organic carbon was increased from 2.4 to almost 3% with the application of nitrogen rate and the switchgrass. However, foot slope had a higher organic matter, which is not surprising because all the nutrient from the upslope they deposit in the foot slope. But this slide shows that switchgrass helped in enhancing the soil organic carbon for the surface depth over the years. And recent data, we just collected sample last year, it was the carbon was more than 3.5%. So bulk density, nitrogen rate did not impact the bulk density because physical property take a little bit time for impacting because of the nitrogen rate. So we didn't find any differences in 2009 and 13. However, landscape position had significantly impacted the bulk density. Foot slope decreased the soil bulk density compared to the upslope and shoulder. Nitrate leaching was not impacted by the nitrogen rates for 2009 to 2015. However, landscape position significantly impacted the nitrate leaching. Again, in our region, the precipitation about like 400 to 500 mm, and it was very difficult sometimes to get even the water sample. But over the year, if you can see that from 2009 to 2015, the nitrate leaching was decreased. So this figure shows the nitrate leaching in 2009 to 2015. It was drastically decreased, and part of the reason that switchgrass started increasing the biomass yield, and that was so some of the nitrate was used by switchgrass, and it helped in reducing the leaching. And this is the switchgrass yield that shows that it's with the high nitrogen, it was a high yield, and that was the reason we didn't have significant differences because the high nitrogen increased the biomass, so it take up a lot of nitrate. Soil nitrous oxide fluxes was not impacted by the nitrogen rate up to 2012. However, higher nitrogen rate increased the N2O fluxes in 2014 and 15. And foot slope position had higher fluxes compared to the shoulder. Again, foot slope position, it was the low bulk density, lot of pores and moisture was there, which enhanced the nitrous oxide fluxes. And again, nitrous oxide fluxes were decreased from 2010 to 15, and this was due to the higher biomass yield and the switchgrass that helped in improving the the soil properties, and it helped in decreasing these fluxes. And another reason why these fluxes are decreased over the years because of the precipitation and temperature. You can see that from 2009 to 2015, it was a little bit decreasing trend in the precipitation and temperature, which helped in decreasing the N2O fluxes. So to conclude, our study showed that long-term application of nitrogen fertilizer improved soil organic carbon and soil nitrate, but it also increased the switchgrass yield and negatively impacted the environment by increasing N2O fluxes and CO2 fluxes to the atmosphere. So our study showed that medium nitrogen rate was the best rate for the switchgrass growth. It was economically higher biomass yield, and environmentally it had a lower CO2 and N2O fluxes. So it was really good. So I would like to acknowledge the producer, Jerry Reutz. We are using his land to conduct our experiments since 2008 and 9. And graduate student, I researched a lot of students and researchers worked under this project, and financially support of this project was provided by North Central Regional Sun Grant Center at South Dakota State University through the Department of Energy. Thank you very much.
Dr. Girish Chopala, who is working in Australia, he told me that he is watching this conference through online, and that means this is really an international symposium. And I think that people from overseas are watching this conference online. And the next speaker is also from Australia. He's Dr. Budiman Minasni from University of Sydney. The title of the presentation is Spectroscopy as a Rapid Nutrient Analysis Method to Address Nutrient Use Inefficiency in the Agroecosystem.
Hi, hello everyone. 안녕하세요. Thanks for your invitation for me to present for the Korean Society of Soil Science and Fertilizer. My name is Budiman Minasni. I'm here in Sydney. I'm going to present to you about my work. So today I will talk about infrared spectroscopy for rapid nutrient analysis to address nutrient use efficiency. So as we all know that plant nutrient use efficiency depending on the efficient or effective nutrient analysis, whether it's nutrient analysis on the plant or nutrient analysis on the soil. So we need to have accurate and rapid analysis about the nutrient status of the plant or the soil so that we can formulate accurate fertilizer recommendation, or we can formulate when or where to place the fertilizer so that we can increase the nutrient use efficiency. But current lab analysis is inefficient. What does it mean? That means that it takes time to take the soil or the leaf samples to send it to the lab and then to do all the analysis. By the time you receive the soil analysis or leaf analysis back, the results back, it will be maybe 1 week or more than 1 week. That means that the plant, if you are if there is a deficiency on the plant, that means it's too late to apply, or if there's an excessive nutrient on the plant, it's also too late. to apply it. So we need for a rapid and real-time low-cost analysis on the plant on soil. So people have been looking at different sensors that can give us a nutrient analysis, whether it's on the leaf or on the soil. So today I will talk about the near-infrared analysis on the leaf samples and the mid-infrared analysis on the soil samples. So we discussed this in the paper recently published in Advances in Agronomy, a review about the use of near-infrared spectroscopy for leaf tissue analysis. So what's the basic? The basic is that the infrared spectrum, or the visible and infrared spectrum, where it hits if you apply it on the plant tissue, so some of it will be absorbed, some of it will be reflected. So the amount that is being reflected, it tells us something about how much is it being absorbed and what is it related to the plant condition. So we can use this to have a more efficient or effective nutrient management. So what do we mean? Like if it's conventionally, for nutrient analysis, we need to go out in the field and sample the leaf. We need to dry the samples, dry the leaf or the soil, and then we need to grind them and then weigh them and then do the laboratory analysis. And finally, we get the results. We put it in plant status information about the plant. And with the spectrometer, we can bypass all of this by directly measuring it in the field, by directly measuring the nutrient in the field, and then the results will be straight away that we can use it in the for the fertilizer recommendation. So in the first study, we want to see that if we just scan on the plant leaf that has been ground and dried, can we estimate nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur as a macronutrient, and also some of the micronutrients that are beneficial for the plant growth. So in this process, we have 375 cotton leaf samples. So 75% is used for calibration and 25% is used for validation. Calibration, that means we build the model, and then 25% is used to assess how good it is. And then we repeat this process 50 times to make sure that we don't get we don't have the probability of getting good representative samples. So these are some of our results. For example, if we see macronutrients, this is all results based on validation. That means the data is not used in the process, in the calibration process. Nitrogen, calcium, sulfur, magnesium, we have R square around 0.9 to 0.94, which is all quite high, and a very low root mean square error. So this is in terms of percent. And also reasonable accuracy for phosphorus and potassium. So that means that scanning just the leaf and getting a good calibration, we can estimate the macronutrients very accurately. So how about micronutrients? So most of the micronutrients, most of it can also be well predicted, but not as high as the macronutrients, especially sodium, manganese, molybdenum, chlorine, iron, copper, and to some degree boron as well. And zinc here is not that well predicted. So so how does the NIR able to predict to estimate the nutrient content? So for macronutrients, if it's related to organic compounds, it can be seen by the refractance on the leaf, because all of it is related to the protein and the organic material bonds that can be detected by the leaf. But some of the inorganic compounds, for example, calcium or magnesium, the infrared can detect it is because there's some association between the organic and the inorganic compounds, so that it's detected via indirect association. And also macronutrient has a higher concentration, so that's why it can be detected much better compared with the micronutrient. So now we would want to take to the further steps so that we know that using dried and ground leaves under standard condition, we can estimate the macro and micronutrient very accurately. But how about directly scanning the leaf with the sensor? So we do another comparison, and then this is the dried and ground leaves, and this is the fresh and removed leaves. And when we compare it, for example, nitrogen and phosphorus, we can see that the root mean square error or the error is almost the same whether you have it on the dried and ground or fresh and removed. Only in some cases, for example, sulfur, that you can see the reduction, and calcium, you can see the reduction in the error. So overall, dried and ground leaves is better than the fresh leaves, but using fresh leaves, the accuracy only reduced by 90% for some micronutrients, and it's only reduced by 11% of micronutrients. So it's the accuracy is still within reasonable, it's still quite accurate enough for a nutrient use management. So why is that so? Because under dried and ground leaves, you can see that the spectra or the reflection is quite prominent. But under fresh leaves, because it has a water on it, some of the signal is absorbed by the water. So sometimes you get a reduce in the accuracy. But actually, when we look at the model, actually the fresh leaf also can compensate the calibration by using a wider range of wavelength, not the certain wavelength, more certain wavelength used in the dried and ground leaves. So as a summary on the leaf nutrients, that all micronutrients can be estimated with high accuracy, and most micronutrients can be estimated relatively high accuracy. There is a reduction if you use fresh leaf compared with dried leaves, so that overall there's a strong potential for use of NIR in the field on the fresh leaves. So now I'm going to talk about infrared on the soils. So previously I talked about near infrared, but on the soil itself, if you look at the spectra, this is the spectra of wavelength of the soil as a function of a wavelength, as this is the absorbance. Under the near infrared, we can see that although there's some spectral signature, under the mid-infrared, there are far more signature of the soil that can be derived, which I'll explain to you later. And a lot of this, the NIR on the other are actually the called the overturn or the reflection of the MIR. So the peaks are not as sharp, and also it's broader and also smaller. So that's why we're going to use the MIR spectroscopy on the soil samples. And this has been suggested even in 1998, more than 20 years ago, that it says that can mid-infrared to replace soil extraction, can we use the mid-infrared to replace lab analysis? The answer is probably some, but not all. But the advantage, as I say, to do with the mid-infrared is that the mid-infrared spectra or the reflectance of the mid-infrared characterize a lot of the minerals components. For example, if you see around the 3600 wave number, you can see this peak is a signature of kaolinite, and this peak is a signature of illite, and some of this peak is a reflection of smectite or montmorillonite. So overall, there are different peaks, and each peak is related to the minerals or organic matter association. So that's why we can detect more properties. But what soil properties can we estimate using the mid-infrared? So fortunately, we have a big database. This is from the USDA Kellogg Soil Survey Laboratory. They have more than 17,000 pattern or profiles with mid-infrared and also lab analysis. So here we can use and we can check whether the mid-infrared can predict a range of soil properties. To do that, first we use a deep learning model. So deep learning is advanced machine learning models where we take the input in terms of spectra, and then the deep learning model has different layers which scan the spectra. look at the spectra and then try to relate this spectra into the soil properties. And it's been used mostly for image recognition. So in this study, we try to use the convolutional neural network, or CNN, to see that if we have a big data set, such as the US data set, can we use it to accurately predict some of the fundamental soil properties. So we compare with the standard method called the partial least square regression. This is PLSR, and the second one is the regression tree method called the QBIS, and this is the deep learning, or the CNN method. And we can see overall the accuracy of the CNN is highest than compared with the standard method, right? But even with the standard method, for example, total carbon, organic carbon, CEC, clay content, can be already predicted quite accurately. So using the deep learning method, on average, we have about 37% more accuracy improvement that compared with the standard method. You can see this in the sand and the pH, the accuracy that the R square 0.87 become 0.95. We use this kind of deep learning method. Based on big data, a lot of data is required. So, but how about other soil chemical properties? At the KSSL database, there's about 100 soil chemical properties that has been measured, so we can test the idea if certain soil properties can be predicted quite accurately. And we compare it on the validation data set as previously. So in the accuracy, we group it into 4 categories, A, B, C, and D. Based on different criteria, I say that we have multiple criteria, so we don't just look at R square, the variance of explained, but we look at also the concordance. How does it agree at the 1-to-1 line? How does the root mean square error compare with the interquartile range? Because some of the data, for example, carbon is not normally distributed. We also look at how does the bias compare with the interquartile range. Using these 4 parameters, we can categorize it. A and B is highly accurate, C is okay, and D is not that good. So A, B is around the R square is around 0.9, C is around 0.6, 0.7, and D is around 0.4, 0.5 R square. So, but we also look at some principles. Our proposition that we, based on our previous work before, is that properties that are related to soil mineral and the organic compounds of the soil and surface chemistry can be well predicted because it has chromophores or signals that are responsive to the infrared. But some that are properties that are related to the soil solution or extraction chemistry cannot be well predicted, which we'll see later. So for example, total carbon, total nitrogen, total sulfur, carbon and nitrogen can be well predicted, but not so much of the sulfur. Sulfur still a lot of, the error is still relatively high, but also different forms of carbon, for example, carbon by potassium permanganate, and also this same enzyme activities, but carbons in the particulate organic matter, nitrogen in the particulate organic matter can be well predicted, but sulfur is still not that good. So for example, this is nitrogen, so this is in terms of total nitrogen, it's well predicted over a range from a small value to around 0.8 or 1%. But sulfur is still relatively large error. And then this is, we look at elemental concentration. That means that after extraction, extraction, this is the total concentration, and we can see that a lot of the element is can be well predicted. So this accuracy is quite high until some of the very low, the one with a small amount. So this is, we rank this in terms of interquartile range. The units is in terms of milligrams per kilograms. We can see some of this, the range is quite small. The one, if you have a small amount, that means that it's unlikely that you're going, for example, this is selenium that is has a low concentration, and some of the element which has low concentration, it cannot well predicted. But overall, if the major element and some of the major trace elements, we can predict it relatively accurate. So for example, calcium and iron can be well estimated, predicted quite well, high accuracy. And also different forms of aluminum and iron, that is oxalate, either is oxalate extractable or dithiamide citrate extractable. Different forms of iron or aluminum for pedological study or chemical studies can also be well predicted. And CEC, this is the exchange capacity of the soil, which is well known to be well predicted. But for some of the calcium and magnesium, it's also well predicted on the cation, the major cations, but potassium and sodium, which has lower concentration, is not so well predicted. And pH is also well predicted. But if we look at the concentration of the element which is extracted under saturated condition, we can see, for example, different forms of nitrogen, nitrate, ammonium, the accuracy is quite low. That means that if the amount that is based on the solution chemistry that are in the soil solution cannot be well estimated using mid-infrared. So unfortunately, some of the nitrate and nitrite cannot be well predicted using the mid-infrared. Similarly, for phosphorus, all these available phosphorus are the water extractable, Bray or also on Mealy. It's the accuracy is not high, but the one that can be well predicted is the phosphorus retention. That means that if you apply a concentration of phosphorus and how much it is being absorbed by the soil, it can be well predicted. And for the Mealy extraction, some of that mostly it cannot be well predicted, but some of the element with a high concentration, for example, calcium and aluminum, it can be well predicted. So this, we can see that the R-square value, the accuracy is depending on the range of the data, interquartile range of the data. So obviously, if you have a high elemental concentration in the solution, it can be predicted. So overall, this is all depends on how you analyze the spectra. So we recently just written a book about soil spectral inference with R, about how we use the spectra, from the spectra, how we convert it into soil properties. So this will be upcoming maybe in next 2 months. So it's published by Springer, and I'm happy to talk to you next time if we have a chance about how to process this data. So overall, as a summary, so NIR on the leaf samples has the ability to estimate both macro and micronutrients on leaf samples. On the soil samples, MIR can also offer a highly accurate measurement of many soil chemical properties, but it have to stress that there are properties related to soil, mineral, and organic components and the surface chemistry of the soils. The properties that are related like to the soil solution or the extraction chemistry still cannot be well predicted. Okay, that's about from me. Thank you very much. And Kamsamida, thank you for your attention. So if you have any question, I'm happy to answer by email. Thank you very much.
아직 그 프레젠테이션은 끝나지 않았는데요. 지금 이사회가 5시에 시작될 예정이라서 이사분들은 지하 1층 인탈 룸으로 지금 이동해 주시기 바랍니다. Let's move on to the next presentation. The speaker of the presentation is Dr. Chang Oh-hong from Busan National University. The title of the presentation is Nitrous Oxide Emission and Nitrifier Communities in Arable Soil Amended with Sulfate Minerals.
Hello everyone. I'm Chang Oh-hong. working at Busan National University as soil science professor. Today, I'd like to share my topic titled Nitrous Oxide Emission and the Nitrifier Communities in Arable Soil amended with sulfate materials. Global warming potential of greenhouse gases. Nitrous oxide is one of greenhouse gases which emitted from the arable soil fertilized with nitrogen. Even though global emission amount of nitrous oxide is lower than that of methane and carbon dioxide, global warming potential of nitrous oxide is much greater than that of carbon dioxide and methane. So when we consider global warming potential of nitrous oxide, we should take action to mitigate nitrous oxide emission from the arable soil. Nitrous oxide is emitted from the arable soil through several microbial processes, including nitrification, nitrite ammonification, and denitrification, and nitrifier denitrification. Denitrification is known to be main reaction to produce nitrous oxide from arable soil. So denitrification is the microbial reduction of nitrate or nitric oxide to nitrogen gas. So under limited oxygen in the soil, the nitrifier switch respiration from aerobic to anaerobic. In nitrate respiration, nitrate functions as an alternative to oxygen as electron acceptor. This figure illustrates electron acceptors that are used by microorganisms at different redox potential. Theoretically, microorganisms associated with denitrification use different electron acceptors for their anaerobic respiration depending on redox potential of soil system. Microorganisms use oxygen at 820 millivolts, and they use nitrate at 740 millivolts, and they use sulfate at negative 220 millivolts. A few previous studies reported that nitrate, sulfate, and iron and manganese can all be in operation as electron acceptor at the same time in the real soil ecosystem. Therefore, we hypothesize the addition of other electron acceptor rather than nitrate might reduce nitrate consumption and nitrous oxide emission, because iron, manganese, and sulfate could be used as electron acceptor for anaerobic respiration instead of nitrate. The objective of this study was to evaluate the effect of sulfate material as electron acceptor on nitrous oxide emission and denitrifier community in soil, and to evaluate the feasibility of the metal sulfate as soil amendment to reduce nitrous oxide emission. In soil microgen test, metal sulfate, including iron sulfate, manganese sulfate, and zinc sulfate, and zero valent metals, including iron, manganese, and zinc, was selected. And nitrogen substrate was potassium nitrate, and selected materials was added at the rate of 0.1% on a weight basis. Incubation test was conducted for 48 hours. And bacteria and denitrifier abundance in the soil were measured using real-time PCR. After that, 16S rRNA amplicon sequencing has been conducted to see changes of microbial community in detail. The microbial community was analyzed using CHIME-2, and difference in the microbial community was analyzed with LabC. In the field experiment, selected crop was maize, and metal sulfate, including iron sulfate, manganese sulfate, and zinc sulfate, was applied at the rate of 50 milligram per kilogram of soil. And this field experiment was conducted for 2 years from 2018 to 2019. And cumulative nitrous oxide emission and yield of dried matter maize ear were measured to calculate yield scale nitrous oxide emission. This table demonstrates the physical and chemical property of the studied soil. This graph demonstrates mean value of cumulative nitrous oxide emission across metal sulfate and metals. Mean value of cumulative nitrous oxide emission across metal was much greater than that of control, but that across metal sulfates was lower than control. The trend of bacterial 16S rRNA copy number with metal sulfate and metals was similar to that of cumulative nitrous oxide emission. Copy number of bacterial 16S rRNA increased with metals, but did not with metal sulfate. Cumulative nitrous oxide emission was greatest with mangan and followed by iron and zinc. Electron could boost denitrification because denitrification is sequentially reduction process that require electrons. Zero-valent mangan is oxidized and provides 4 electrons. Iron provides 3 electrons and zinc 2 electrons. So metal that provide more electrons could produce the more nitrous oxide. This is the reason why cumulative nitrous oxide emission with manganese was the greatest. Cumulative nitrous oxide emission decreased with iron sulfate, manganese sulfate, and zinc sulfate compared with control. Metal sulfate did not affect copy number of nitrite reductase near S and near K, and nitric oxide reductase nor B. There was no significant difference copy number of near S, near K, and nor B among the metal sulfates. However, the copy number of nitrous oxide reductase nor Z decreased with metal sulfates. Nitrous oxide reductase is an enzyme that reduces nitrous oxide into nitrogen gas and decrease nitrous oxide emission. In this study, metal sulfate decreased the copy number of nitrous oxide reductase nor Z. Therefore, nitrous oxide emission should have increased with metal sulfate, but it decreased with metal sulfate as shown in the previous graph. This means there was another mechanism to decrease nitrous oxide emission rather than nitrous oxide reductase nor Z. As you can see in this figure, the trend of nitrate consumption with metal sulfate was opposite to that of sulfate consumption. The trend of cumulative nitrous oxide emission was opposite to that of nitrate consumption. But it was similar to that of sulfate consumption. This implies sulfate was consumed by microorganisms associated with denitrification instead of nitrate. Subsequently, nitrous oxide emission decreased with sulfate. As shown in this figure, the copy number of sulfate-reducing bacteria, DSRA, was much higher with metal sulfates than that with zero-valent metals. According to amplicon sequencing results, in alpha diversity analysis, there was no significant difference among the treatment. However, in beta diversity analysis, there was significant difference among the treatments. So we identified the microbial diversity was affected by metals and metal sulfate material treatments. In cladograms analyzed by LabC, green color indicate predominant microbial community in metal sulfate treatments. Among these communities, Microcilliaceae and Acidibacter and Gentomonadaceae increased with metal sulfate treatment. Those bacteria was identified as sulfate-reducing bacteria. This implies sulfate was consumed instead of nitrate by sulfate-reducing bacteria associated with denitrification. Subsequently, nitrous oxide emission decreased with sulfate. In two-year field test, mean value of cumulative nitrous oxide emission across 2 years decreased significantly with metal sulfates. For 2-year field test, there was no toxicity symptom in maize, and application of metal sulfate did not affect yield of maize ear. So maize yield did not decrease with metal sulfate for 2-year experiments. So mean value of yield scaled nitrous oxide emission across 2 years decreased significantly with metal sulfate. This implies the application of metal sulfate could reduce nitrous oxide emission per unit of maize grain production in the viewpoint of economic viability and environmental conservation. Take-home message. So cumulative nitrous oxide emissions significantly decreased with sulfate materials. There was no significant difference in denitrifier abundance. The sulfate consumption and DSRA abundance dramatically enhanced with addition of sulfate materials, and sulfate could play a role in electron acceptor instead of nitrate to reduce nitrous oxide emission from arable soil. So the sulfate material could be a soil amendment, reducing nitrous oxide emission from arable soil without decreasing productivity. Thank you for your attention.
Dr. Muhammad Saiful Islam Rian from Sher Bangla Agricultural University, Bangladesh.
Welcome to my presentation. Today I'm going to talk about the title of that, title of that is Knowledge-Based Nitrogen Application, a Boon in Rice Systems in Bangladesh. You know, Bangladesh is a densely populated country, and it is situated on one of the largest and most complex deltas in the world. Around 40% of land below 13-meter elevation. Cultivable land, forest, water bodies have been decreased. However, in recent past, Bangladesh achieved the third position in accordance with the rice crop production, just defeating the Indonesia, just behind of India and China. How come Bangladesh achieved this level of achievement, although Bangladesh has a very small country? There are three main reasons behind of that. If you see in this slide, almost 80% land are occupied with rice production, and then there's another reason is that the cropping system. If you see in here that single crop, double crop, triple crop, quadruple crop, this cropping system is applying in our country, especially for rice systems like Aush, Amon, Boro, 3 seasons crops, which is called triple crop. And even if you see in this next plate in here, along with the Aush, Amon, Boro, sometimes we grow a short period of crops like mustard or some sorts of vegetables. And the main reason why Bangladesh achieved that much greater level of rice production is the fertilizer utilization. If you see in this graph, Bangladesh superseded India in 1995 or 1997, in between this year. And even the trend, whatever we have seen in here, if you see in the second plate, the trend is mostly similar with fertilizer consumption. From that graph, we may say that nitrogen utilization helps Bangladesh to reach that much productivity, especially the rice production in our country. Besides this, in Bangladesh, the fertilizers, nitrogenous fertilizers is being used. For example, prilled urea, urea super granule, or urea mega granule, NPK briquette, and PKS mixed fertilizers, diammonium phosphate, ammonium sulfate. If you see in here that with time passes, the utilization of fertilizer, especially the nitrogenous fertilizer, the urea demand is increasing constantly. The thing we need to consider this graph, because the scenario what we are going to be faced in near future, that the yield is not constantly increased. Although the last slide, if we have seen that it is constantly increased, but the yield is not increased with that rate. If you see the first bar graph in 1980, although we used that time only the 80 kg nitrogen per hectare, but that yield was around above the 6 ton. Even 2015, the yield is almost same, although we use above 140 kg nitrogen per hectare. That means we can assume that in coming future, near future, our country's rice production could be stagnant or could be declined. So we need to consider these things right now, because although we are applying a lot of fertilizers in the field, but the return is not coming in that way. So therefore we need to think about it. And besides, if we use or utilize next level of fertilizer, it also brings negative environmental consequences. For example, eutrophication or ozone layer depletion, or like human health, like blue baby syndrome. These sorts of things is coming if we use the excess. And even we know that after applying the nitrogen fertilizer in the field, there are 4 phases like that. Especially in the rice field, after applying the nitrogen fertilizers, it transforms into the ammonia through the mineralization, and part of the ammonia it lost through the volatilization, and part is being used by plant, and part of that through the nitrification it also transforms into the nitrate, and end of the day the nitrate is being leached through the leaching process, and even the denitrification, the gaseous product like dinitrogen, nitrous oxide or dinitrogen, it also occurs. So if I take this ammonia and this source of gas is one way loss, and another is leaching, and a third fate what we are considering, that it would be happen just when the excess nitrogenous fertilizer is mixed with the water or precipitation, it's just washed out from the field. So these 3 processes are 3 phases like washing, leaching and gaseous loss are negative. But what is the positive? Among the 4, the take up by the plants, but the rate is too low. Like we can say that 30% of nitrogen is just used by the plants, and rest of 70% is just washing through these 3 processes. Therefore, in our country, we try to develop some process or some practices which could be used to reduce the wasting the nitrogenous fertilizers. For example, in our country, we have been practiced like deep placement of urea supergranule or urea mega granule. Then these are the deep placement system in here you can see, and then sulfur or neem coated urea, then bioorganic fertilizers like vermicompost or trichocompost, and then there are some varieties they need less quantity of nitrogenous fertilizer. Those are the couple of process we have been using in our country based on our knowledge and all the things. Among them, the top one, this is the best, and they provide, this process provide the better yield, better management and better outcome. How come it would be the appropriate, or or we can say better? Because in the USG, that means urea supergranule process, the system is the briquette. It needs to be set into 7 to 10 centimeters depth. As a result, the USG has less chance to come contact with the oxidized soil zone, and thus there is a less chances to ammonia volatilization, and even as after mineralization, urea transformed into the ammonia and it fixed with the soil or clay particles. So it sustain or remain a longer period compared to the just spill or broadcast urea. And even as it is fixed with the soil, it has less chances to transform into the nitrate through the nitrification. So as it is the transforming into the less quantity of nitrogen, there is a chances to less leaching, and even less nitrate, that means less denitrification. So we can control all the things. And even if you see in here that as this one is not coming directly contact with the stagnant water or irrigation water or excess precipitation water, so therefore the chances of washing with the of nitrogen fertilizers through water is less. So if you see in here, we can control many things by this system through USG. And in addition to, as this system USG is putting close to the root area, that means rhizosphere, so the plant, that means rice plant, can accumulate or they can use the nitrogen longer periods. So as a result, their vegetative growth developed vigorously, and substance or end of the day the production will be also increased. we can say that through this system the nitrogen rate is comparatively less if you see the yield, but how much we can get lesser quantity of nitrogenous fertilizers. So if you see in here that it's a normal rate in the briquettes, that means the guti in our Bangla word we call the guti, the rate is 62,500 per hectare. So based on that, for transplanting almond or boro, transplanting almond it needs the lower rate of fertilizer compared to boro, and if we take the 1.8 gram per guti, then the fertilizers is required for 52 kg. However, for boro, as it is required little bit higher quantity compared to tea almond, then it also it needs almost 78 kg. So based on the recommended dose for tea almond and for boro, if we subtract the things, we can find that the result in here. Based on that, we can say that almost 50% less nitrogen is needed through the UHG system or UDP system. Besides the grain yield, if we consider the grain yield through the prill urea, UHG and NPK briquettes, we found that over the control or even the compared to prill urea, the UHGs provided the greater level of grain yield and straw yield as well. So not only this, but also it also provided that NPK briquettes also provided the greater yield and straw yield. In addition, we can see the nitrogen recovery and nitrogen use efficiency. Nitrogen recovery means that the nitrogen accumulation by the grain and straw, and even nitrogen use efficiency just with the grain compared with the applied nitrogen fertilizers. In that case also we can see easily that compared to control and prill urea, UHG, if you see it's a noticeably higher use efficiency, either recovery or nitrogen. So that's a good finding in here. And even the ammonia volatilization, our earlier slides, we have seen that ammonia volatilization, the UHG system can be controlled. But in here, if you see that the prilled urea, that means the broadcasting urea, they produced, or the ammonia flux was much higher what we have seen in the urea briquettes. So besides that, ammonium nitrogen concentration also higher in the broadcast systems compared to UDP. In UDP, if you see almost control level, there is not much more ammonium nitrogen. And the one greenhouse gas like nitrous oxide and nitric oxide, what is the pollutant? If you see in here, it's very clear that prilled urea, they provided the greater level of nitrous oxide or nitric oxide. Even one gas, what is we call the rice fields, the main hub of the greenhouse gas is called methane. Even the methane emission also much more lower. If you see the displacement is on the dotted line, in every cases the methane emission is much more lower than what we observed through the urea broadcasting. So even the carbon sequestration and total nitrogen content through the UDP system is much more higher. If you see in here, urea, UDP is here. In every cases, the carbon sequestration and total nitrogen concentration is higher through the UDP system. And then if I consider the economical benefit, we have seen from this graph is very clear that we can make money through the UDP system. If I take just one example in here, under the UDP, we can achieve the $560 per hectare, whereas the through broadcasting system it's the $430. So from this graph we can easily guess how much financially benefit we can achieve through the UDP systems. So the sum of the things in here, we can say that through the UDP system, the rice grain yield, financial benefit, carbon sequestration increased, and simultaneously the nitrogen loss reduced, nitrogen fertilizer uses also decline, and interestingly the ammonia, methane, nitrous oxide, nitric emission also decreased significantly compared with the broadcasting urea. If we concise the further the outcome and we can rate the level what we have been practicing UDP in our country, we can say that mitigation level is very excellent, low cost excellent, income we can say the good, but adaptation it's not good, it's poor. So why it's happening? Although we have seen lots of benefit in every cases, but why it's not adapted in here? There are main two reasons behind of that. If we see in this slide that for displacement of USG, it will take longer time and higher level. Although recently the Bangladesh Agricultural Rice Research Institute, they developed one USG applicator which can be saved almost 2/3 time and level. This is the one big problem. Another problem is the policy making, especially the business syndicate, because as we know already that through the USG system, urea requirement is compared to the less. So as the less fertilizers is needed, so they cannot make the more money. Therefore, the businessmen, they never inspire the farmers or growers to use the USG system. So this is another barrier. We need to give concentration for developing the USG applicator, even to convince the businessmen to get them understand that how much benefit we can use these things, and we need to make them understand. And finally, I may say that in here that although we have achieved that much benefit through the USG system in our country, in Bangladesh, but what happened across the world? We need to justify the USG system any other part of the world to getting the concrete result, whether we have achieved the higher or lower or similar level of findings. So that's all for today. Thank you very much.
Now we are going to wrap up the session of the day. Once again, I thank all 7 speakers in this session for giving us nice presentation, and also thank you all for attending the conference. And I hope you enjoy the rest of the program in this conference. Thank you.